centers, local coordinators, participants at all of the nodal center, ladies and gentlemen, participants in the studio, myself, Dr. P.P. Chaudhary, I'm coordinator of this program on behalf of this institute, and being the coordinator of this program, I welcome you all for this 5 days program on advances advances in optical fiber communication technology. So I hope all the centers are connected to the studio, and everybody, you can hear to me. So we all know that communication, now it has become a universal truth that communication, it was needed, it is needed, and it is need of the future. So without communication, it's very difficult to now in the present day society or technology, it is very difficult to survive. And that's why I mentioned that it is now a universal uh, way of communication. So now time is over when the communication was only limited to the voice communication. Now we need the communication in terms of the voice communication, the communication in terms of the data communication, communication in terms of the video communication, and of course we may call it the multimedia. As a result, we all come across different type of technology. We started with 1G technology, 2G technology, 3G, 4G, and even 5G is coming. So all now our requirements is not only the communication, only the voice communication, but the need is to communicate each and everything. So as a result, we need a communication system. The communication system which were existing in 70s or 80s or even in 90s are now not able to fulfill this requirement. So it is a ever increasing demand globally, and as a result, our communication system need to be a very powerful. So in order to fulfill all the technological requirements, it is the optical fiber communication. So optical fiber communication is the technological route to achieve this ever increasing goal. So as a result, this course is planned for these 5 days on the advances in optical communication technology during these past, I think 30 to 35 years. Lot many changes had taken place in the optical fiber communication. You know, the first fiber optic communication is started in 1977 when the telephone signals were sent over the optical fibers, and with the passage of time, so many changes has been taken place. We come from a point to point link, we move to the multi-channel links, we talk about the WDM technology, DWDM technology, then optical communication. Now, when you have a optical signal, it has to be amplified at different stages. We all know that in a communication, there are two important issues. One is the attenuation, other is the dispersion. So all these things have to be managed because communication needs are increasing day by day. So as a result, the system needs a lot of refinements, and of course, when you are adding more and more data to your channel, different type of problems crept into the system. So we have to also look for those issues. So in this program, we will discuss all these issues. So I hope everybody have the copy of timetable. I sent the schedule of timetable to all the participants. So I will display it here. If anybody has not got that, Okay, so I hope everybody got this schedule. Advances in OFC technology. The course will be from 19 to 23rd December, and this program will be conducted with the various lectures from different studios. So we have around more than 12 nodal centers for this program. They are in the state of Punjab. We have centers in Haryana. We have centers in Rajasthan. Centers from Tamil Nadu, Chennai, centers at Odisha. So almost more than 12 centers have been connected for this program. And I hope all the center they have good audio video connectivity. And before we go for the introduction part to the program or inauguration part, let me first discuss the timetable but I have planned for this program. So this session will be registration and inauguration session, which we are continuing. And then the second session will be on OFC technology and overview. So I will give an overview, but how the technology has started and how the systems have developed, what are the limitations and what are the future advancements in the technology, future needs and future advancement. So I will engage this session. So then we will find that in every optical fiber communication, we have the optical source, we need the optical receiver, or what you call optical transmitter and optical receiver, and the channel here is the optical fiber. So optical fiber or optical fiber cable. So the main propagation is through the optical fiber. So in the second half, I will engage another session on optical fiber waveguiding. So we know the light, it is a particle as well as wave, so dual nature of light, but here it is the wave which is important. For propagation part, these are the electromagnetic waves. So all the carrier, they are the electromagnetic waves. So again, here we have the optical wave, which is a carrier of the information. So we will discuss about what are the how the light is propagated in the optical fiber, because it is the propagation which is important. So we will discuss various fundamental parameters and different parameters which are associated with the optical fiber, and then different type of fiber communication. It is not only that we have only one type of fiber, different type of fibers are there. They may be required under different requirements. So I will again give some idea about the light propagation, fiber configuration, and different fiber parameters. So this session will be from 2:30 to 4:30. So then on Tuesday, we have another session on transmission characteristics of optical fibers, or also we may also call it as the signal degradation, because it is a signal which travel in the optical fiber, and we all know when electromagnetic energy travel in any medium, it get attenuated. The power, there is always a power loss, and there is always, since it is optical signal, there is always a dispersion. So light has inherent property of power loss and the dispersion that lead to attenuation of the signal or broadening of the signal. So we call it as the signal degradation. So I will again engage this session on transmission characteristics of optical fibers. Then we will engage another session on laboratory demonstrations. Earlier the session was planned in the afternoon. Mostly as conventional in our education system, we have lab sessions in the afternoon, but due to some technical problem, it is not possible to have another session, theory session in the morning. So we will demonstrate different type of optical fiber, different type of basic fundamental experiments with optical fiber related to communication in the second session. So that will be basically attenuation, how much data, bandwidth or dispersion, all these parameters we will demonstrate. And Miss Navjot Kaur, she will associate me in engaging this session. So this session will be live in the studio in terms of the demonstration. Then afternoon session will be on optical sources and detectors. So we all know that we need a optical transmitter for any communication system. We need a optical receiver, And in optical communication, the data is optical signal. It is a optical data, and in order we only convert electrical data to optical data. So a electrical signal is converted to an optical signal, and this job is done by an optical source. So basically we modulate a optical source. Similarly, the optical signal travel in the optical fiber, and at the destination, again, we receive the optical signal. This optical signal is received by the receiver, and depending upon the requirement, it may be amplified, and ultimately it is converted from optical form to the electrical form. So all the processing is in the electrical form, because we need at our destination, our telephones, our instrument, they will respond to the electrical signal. So ultimately, or whatever information is there, it is basically the electrical form or electronic form. So we need the sources and detectors for this purpose. So modulation and demodulation, all these jobs are performed by the optical source and optical detectors. And for this session, engineer Randeep Bhatnagar, Mr. Bhatnagar from CSIO. It is a Central Scientific Instrumentation Organization. It is a CSIR organization. So he is working there in the area of photonics, and he will engage this session on optical sources and optical detectors in the afternoon of 20th December. So then on Wednesday again we will start at 9:30, and now up to this part you will be familiar with that. We have the optical source, we have the optical detector, we have the optical fiber, which are the basic constituents of optical fiber communication system. The rest of the data, what is happening in the background, it is same, whether it is a electrical system or it is a optical system. So all data formulation, data formats, all these are the same. Only at the intermediate state we convert electrical signal to optical signal. This optical signal propagate through the optical fiber, and ultimately it is received by the detector. Again, it is converted from optical to electrical. So now we have to go for the OFC link, OFC system design and analysis part. So we have to put these components in the integrated form, or we have to integrate all the components so that the system should be efficient. So the design part, there are always certain goals. A designer, he always design a system with certain goal, and the major goal is what is the distance for haul, whether it is a short haul link, it is a medium haul link, or it is a long haul link. So certain goal is there in terms of the destination. Then another parameter is the data rate. What is the data rate? At what data rate the system should operate? It may be kbps, it may be mbps, or it may be gbps. So this factor is also there, and according to this requirement, one have to design the system. Because now it is not only the system, it is the economy which is playing a very important role. The system has to be reliable, system has to be high capacity system, and system has to be economical also. And all these systems, they work at certain rate, with certain tolerance power, but you call at the bit error rate. Mostly now the systems are the digital system. Earlier we have the analog system, but now these are the digital system. So we measure either in terms of the bandwidth, how much is the bandwidth provided by the system, and what is the maximum permissible data rate at certain bit error rate. Because whatever system it is, some error will always be there. So because of the many limitations, many inherent problems, so there will be certain errors. So it depends what is the tolerable level of error. So bit error rate is the parameter. So during the design parameter, we have to design the system, we have to check the system, we have to analyze the system. It is not only the design part, but the system should be operational. System has to be monitored all the time. So we analyze the system with different instrument, with different parameters, so that it should operate operate for the purpose for which it was designed. So this again, I will again this session design and analysis of OFC system. So, and then the second session again. So after the first session, daily there will be a tea break for 15 to 20 minutes. Then the second session will start at 11:30. So when you have a communication system in place, now we know when the signal travel, it is always attenuated. There is a power loss, and it is always broadened. There is a pulse broadening. So if there is a pulse broadening, data rate will be affected. If there is a attenuation, the signal will not be able to reach at the destination in good quality. There will be not a good quality signal. So as a result, we have to perform some modification on the system. So if there is a attenuation of the signal, basically it is the power loss. So we have to go for the amplification. In any conventional system where there is a power loss, we have to enhance the power and we use the amplifiers. So in electrical system, we have the electronic amplifiers, well established, but here the signal is the optical signal. So earlier one used to convert the optical signal to electrical signal, then amplify it using the electrical amplifiers, then again convert the electrical signal to optical signal. So when there is a conversion from optical to electrical or electrical to optical, and we know the conversion is not very efficient, or it may be not be 100% conversion. There may be certain loss of the signal at all the stages. So if you, and in a link, if it is a long haul link, number of amplifiers are used, and at every stage there is always a loss of the signal, and there is always a addition of noise from the amplifier. All amplifiers, they have different type of noise, they will be added to the system. So as a result, electronic amplification is not a viable for this system when you have a optical signal. So in optical signal, one prefer that there should be the optical amplification. So we have the optical amplifiers. So for this session, Dr. Umesh Kumar Tiwari, he is also senior scientist at CSIO. So he will engage this session. So he will discuss about different type of amplification techniques and different type of amplifiers, and mostly he will concentrate more on the optical fiber amplifiers, because nowadays these amplifiers, they are designed over the fiber itself. I will mention in the session that now we prefer that it should be all optical network. Everything has to be over the optical fiber because of the compatibility problem, because of the coupling loss problem, and then because of many other issues. Because fiber is very thin, we want that everything should be on the optical fiber, and the signal should be optical signal at all the stages. Whenever we go from optical to electrical, we know the electrical signal cannot provide you that bandwidth or that much speed as the photons can provide. So as a result, optical amplification of signal is required at different stages. And again, in the afternoon, we will demonstrate. We have planned the laboratory session, and we will discuss about all the OFC systems, then analysis part, bit error rate, different parameters which are required to monitor the optical fiber communication system. So again, this will be a session from 2:30 to 4:30, and all demonstration session. So then on Thursday we have another session that is on WDM and DWM system and components. So the system I mentioned as the OFC system, it is a point-to-point link. Mostly our optical fiber communication, it is a point-to-point link because of the limitation that light cannot travel long distance, or it cannot travel just like radio and microwaves because of the many attenuation and scattering or diffraction issues in the light signal. So as a result, the optical communication is mostly a point-to-point link, but it is not that it cannot be a wireless. We have mostly we call it as the free space optics. Light communication is used in the free space to communicate from satellite to satellite and communicate from the tall buildings. So it is only the issue that the light signals even the which is used in the communication, these are the lasers, and the laser, they cannot be sent just like our radio and microwave, because otherwise it is a harmful laser. They are highly focused and they are very harmful. If a laser light fall on the eyes, so it can cause a permanent damage to retina. So as a result, as a policy measure, it is not preferred at the you say just like the microwaves or radio waves. So WDM, DM, the systems, basically these are the multi-channel systems. So we can send number of wavelengths on the optical fiber. Number of different wavelengths can be sent simultaneously on the optical fiber. Because the wavelengths are different, they will follow different path. So as a result, WDM or DWDM, these are the wavelength division multiplexing and dense wavelength division multiplexing systems. So these are the multi-channels. Number of wavelengths can be sent over the optical fiber, and each wavelength will carry different data rates. So as a result, it is a multiplication of the data, because we have the huge data, and sending the data on a single fiber at very high data rate lead to many problems, many impairments. So you need, if you have a single channel, you want high data rate, it means your pulse bit will be very narrow. You need nanosecond pulses or picosecond pulses or femtosecond pulses, which are difficult to generate. So as a result, it is preferred that to operate the system at low data rate, but multi-channel system. It is just like the expressway or lane system on the transport system. So it provides an expressway for the communication system, but it is not that so easy. So we need number of components also. So we go for the multiplexing. So the different number of wavelengths, they are multiplexed, and then at the receiver end, they are the demultiplex. So we have to multiplex the data and we have to demultiplex the data. So as a result, we need different components like different multiplexer, different couplers. So all these are the optical components, and they will be discussed in this session. So I will engage this session on WDM and DWDM systems. So when this system operates, we know the optical fiber is very thin, of dimensions of the order of micron. So when number of channels travel in the optical fiber for specific data rate, we have to maintain certain signal to noise ratio. So some minimum power is required. So as a result, the power per unit area, we call it as the intensity. So there are different intensity effects in the optical fiber. Mostly our systems are linear. We are very comfortable with the linear system. But when the intensity becomes very high, system becomes non-linear. So as a result, non-linear effects, they cause so many problems in the optical fiber communication, because it is a requirement. You have to keep minimum signal to noise ratio. So as a result, when the number of channels are more and fiber is same, so intensity becomes very high and non-linear effects comes into the picture, and we have to again look for the issues, and we have to again see how we can mitigate these non-linear effects. So for this session, Dr. M.L. Singh, he is professor and head Department of Electronics Technology at Guru Nanak Dev University, Amritsar. So he will engage this session on non-linear effects in OFC and mitigations. Again, in the afternoon, there will be a laboratory session that will depict about the WDM and DWM systems and different how to assemble the system, and many other practical aspects of optical fiber will be covered in this session. So then again on the Friday there will be another session on OFC systems, simulation and performance evaluation. Now optical communication system, which if you come across, you see these are the systems which are laid all over the globe, and these are the long haul systems, not practically possible to simulate or demonstrate in the laboratory. So as a result, nowadays we have the many, with the benefit of computer, we have the simulations. Large number of simulation software are available, and we can simulate this system in the laboratory, and we can check the design and performance of the system in the laboratory session. So again, I will demonstrate this session. I will engage this session on simulations and performance evaluation. So we will discuss different type of simulation, different companies. Some commercial software are available in the optical communication. Some are from the RSoft company, OptSim. We have the Opti systems. We have the BPI system. Different. These are very, very powerful simulators which can be where we can simulate the system and we can check the performance evaluation before ultimately going for the hardware developments. So I will engage this session. Then another second session will be on OFC networks and radio on fiber. Now it is the time of networks. Earlier we were having local links. Now we have the different type of link. We have the internet. We have the metro area network. We have the local area networks. All networks are required. So in the networking, earlier we have the networking maybe with the on the copper cable. Now we have the optical fiber network where the huge data can be communicated, and we know the network technologies. And now we can also use the radios. How the radios signal can be sent over the optical fiber. So there is a technology radio on the fiber. So this session will be engaged by Dr. Baljeet Kaur. She is assistant professor at Guru Nanak Dev Engineering College, Ludhiana. So she is expert in this area. She completed her PhD in area of OFC networks, and she will come and engage this session on the OFC network and radio on fiber. So these are the topics which I have planned for this program, and I hope different experts, they will come here. We will have good connectivity, and in the afternoon we will again, after covering all these technology related session, there will be again group discussion and validation about what we have discussed, and we will get feedback from all the participants, how we can improve the program, but other topics can be added to this program so that they can be covered in future of these programs. So this is what I have planned for this 5 days program, and I have tried to cover most of the topics which form the basics as well as advanced area in the optical fiber technology. I hope you all agree with me, or will be happy to have all these sessions in this program. And it is not possible to cover each and every area of optical fiber communication in this 5 days program, because it is a full subject in our engineering curricula, and it's now a full-fledged area of photonics where all these aspects can be discussed. So this is what I have planned for this program. So now we will go to our different nodal centers to have their interaction with all these centers. I request all the local coordinators to be brief, to give input, give the introduction of their nodal center in just 2 to 3 minutes. We have more than 12 centers connected for this program. So I request all the coordinators to be brief, and within 2-3 minutes just complete their introduction about their center. So I will move to the first center. Yes, JSS Academy. So first center is JSS Academy of Technical Education, Noida.
Hello.
I request local coordinator Dr. Deepak Kumar.
Hello.
Please come on the camera. And
hello.
Yes, hello.
Hello.
Dr. Deepak Kumar.
Yes, sir. Good morning, sir.
Good morning. Please introduce about your center in 2-3 minutes. And if you have some dignitaries from your institute, he is also most welcome to address the session.
So we are from JSS Academy of Technical Education, Noida.
Yeah.
And we have a chief guest, Dr. O.N. Pandey, Professor O.N. Pandey. He is the HOD of IC department. Yeah. And we have Professor Z.K. Ansari, which is HOD of Mathematics department here. and Professor O.N. Pandey is the chief guest for this particular function. And
welcome the chief guest.
Professor O.N. Pandey is the HOD of IC department, and this course is beneficial because we are teaching OFC in multiple semesters, including first year, and we are looking forward for the laboratory demonstrations because it will be helpful for our faculty members to pass the knowledge to our students in a much deeper level. And I hand over the mic to Professor O.N. Pandey for a few words.
Good morning, sir.
Good morning.
I welcome dignitaries on your dais, and I appreciate for this course because as Dr. Deepak has explained, our syllabus is also having fiber optics, and this is latest state of the art which you will be teaching. We will be able to convey to our students, and I want a great success for this program so that our faculty can take the benefits. Thank you, sir.
Thank you very much. Dr. Deepak, how many participants you are expecting for this program?
So we have around 15 participants from IC, EC, and physics department. Okay. And we are looking for, because we are in the middle of our external examinations, so we will try to get more participants later on.
Okay, thank you very much for the introduction. So we move to the next center, that is the Global Institute Amritsar, and coordinator is Neetu Gupta. Global Institute Amritsar. Good morning, Neetu Gupta ji.
Hello, sir. Hello, everybody.
Hello.
Am I audible?
Yeah, you are audible. Please continue.
So definitely this fiber optic techniques are very useful nowadays. And the best part which you suggested in your timetable is the practical session. And definitely our faculty and our staff will be benefited through this WDM techniques, that is the wavelength division multiplexing, because such type of practicals are generally not available in the institutes. So because these are the very costly equipments, and by associating with this NITTR, definitely we will be having a chance to get all the practical aspects of the WDM. Thank you very much.
Thank you. And who is the local coordinator for this program?
Professor Neetu Gupta. She is with us. She is the HOD of our Electronics and Communication Department.
Good morning, ma'am.
Good morning, sir. I am Neetu Gupta, and he is our director, sir. And we have approximately 50 participants.
Okay. And I welcome the director of Global Institute Amritsar for nice word for this program. So we will continue with the session with the further introduction of other centers. Now we move to the another center, that is SRMS College of Engineering, Technology and Research, Bareilly, UP. SRMS College of Engineering and Technology. Miss Nazia Parveen.
Good morning, sir.
Good morning, ma'am.
This is Nazia Parveen. Sir, we have our principals are with us and the heads of various departments who are joining us, along with the faculty members from all the departments, including physics. So I would request our principal, sir, Dr. A.K. Srivastav, to say a few words about this session. We have attended one more FDP on same on microcontroller in September from NITTR. It was very beneficial for us. So we are looking again to learn more from this session. I would request principal, sir, to say a few words about this FDP. Thank you.
Thank you, sir. I welcome you, and please say a few words about this regarding this course. Your expectations from this program.
Good morning, sir.
Good morning.
I am Dr. A.K. Srivastava, principal of this college, and I feel that these type of program are really beneficial for us. We are having around 20 faculty members who are presenting right now, and more faculty member may join in the different sessions. We are expecting that such type of session will help us to learn the practical aspects along with theory also. And thank you for such type of initiatives. And we remain connected with the NITTR Chandigarh also in previous sessions. And we are expecting more program in different technology area.
Thank you, sir. And we will try to fulfill your expectations from this program. So thank you for the introduction. I go to the next center, and that is Gandhi Academy of Technology and Engineering, Berhampur, Odisha. May I invite Dr. Mr. Bipan Chandra Mohanty to enter regarding the program. It is the gate, Berhampur, Odisha. May I invite program coordinator Professor Bipan Chandra Mohanty. Good morning. I'm audible at your place.
Okay, sir. Thank you.
Yeah. You continue, sir, please.
Okay, sir. So I am from Gate Barampur. So first of all, I give you many thanks for this program, because this is the technology that is required highly for our engineering faculty members, as well as for the technology that has been developing day to day. As we have communicating our students with the communication subject as a top technology that has been day to day advancing in our communication field. And as I am a communication teacher, I am also introducing to our students for the advanced communication system that has been implemented day to day for the 1G, 2G, 3G and 4G, like the advanced 5G communication system. And this optical fiber is most requirement for the students, as they know the communication, but how the communication system that has been implemented by the systems by using the optical fiber system, and the fundamental requirements for their understanding. This is highly essential for this program. So I am inviting all my branches, and also inviting other periphery engineering college staffs for their benefits. And we have also arranged around minimum 32 staffs. So I give you thanks you for this program. Okay, sir.
Thank you very much. So thank you for your words. And now we will go to the next center, and that is the School of Computing Science and Engineering. They are not connected? Okay. So our next center, we have some problem, technical connectivity problem. Now we move to the Rajasthan Institute of Engineering and Technology, Jaipur. Rajasthan Institute of Engineering and Technology, Jaipur. So may I request Ms. Manisha Agarwal.
Good morning, sir.
For this program, you just introduce about the center.
Good morning, sir.
Good morning.
Manisha Agarwal here. Yes, sir, from RIT College, Jaipur. We have here Chief Guest Professor Kapil Dev Sharma, Dean Academics, RIT. We have Professor Dr. Saroj Kitanwal, Principal RIT, and the various HODs from EEE, MECS, IT. So we have also, sir, I want to tell you that we have earlier also in this year, we have one program conducted first area of research from EC department, which was really beneficial for the faculty. And the same we are looking forward from this session of optical fiber technology, as optical fiber technology is developing a great advance in this field for communication. So we are faculty are looking forward to have a knowledge of it and impart the same to our students. So we are great to be a part of this. Thank you, sir.
I welcome principal and HOD and faculty of the college, and I request principal of the college to say a few words about the program.
Yes, definitely, sir. Definitely, sir.
I welcome you, sir.
Hello, good morning, sir. Good morning, all the participants and dignitaries also and various colleges. And we are really very thankful to Mr. Chandigarh that we are getting benefit out of this. Several programs are here also. Around 7 programs we have conducted in the last session. We have attended in the last session, and faculty get benefited out of and if faculties get benefited and students obviously get benefited and society itself. So we are really thankful, sir, and we want series of such type of workshop we will conduct in future and will get benefit. Thank you, sir.
Thank you, ma'am, for introducing the center. We will continue with the program. So we go to the next center, that is RD Engineering College, Ghaziabad. RD Engineering College, Ghaziabad. May I invite local coordinator Mr. Harshvardhan Bist to introduce about the center.
Yes, at RD Engineering College.
RD Engineering College, Ghaziabad. RD Engineering College, Ghaziabad.
Yeah, good morning, sir.
Good morning, good morning.
Good morning. Sir, we do have 10 members here right now who are attending this FDP program.
You are Mr. Harshvardhan Bist?
Yeah, I'm just speaking.
Okay, continue please.
Yeah. Yeah, there is a disturbance in the video system right now here. So.
But you are audible here at our place.
Sir, I'm audible.
Yeah,
yes,
yeah.
This is audible. So it's a very good opportunity for me just to be the part of this FDP program organized by your organization. I think it's a very healthy initiative from your side just to enhance the knowledge on FDP, on optical fiber communication. And I feel that, I expect that from this we will just enhance the knowledge of our student by attending this year program.
So, thank you very much.
You're welcome, sir.
So I hope we will be connected.
Yes, sir.
In this manner in other session also.
Okay, sir. Thank you.
Thank you for the introduction. So I will move to the next center.
So they have some technical issues at Margam.
उनका नहीं हो रहा कनेक्ट. ओके, तो नॉर्दर्न इंडिया में चले.
ज्ञान ज्योति को.
नॉर्दर्न. ओके. बाकी भी है ना. So now I will move to the next center, that is the Gyan Jyoti Institute, Banur, and I invite local coordinator Shri Sarad Sharma, Mr. Sarad Sharma, to introduce about the center.
Good morning, sir. Gyan Jyoti College. Sir, we have around 16 participants from our college from 3 departments. They are CSE, ECE, and Electrical and Electronics Engineering department. So basically, we feel privileged to be a part of this session on optical fiber communication, advances in optical fiber communication. Basically, optical fiber is used for by many telecommunications companies to transmit telephone signals, internet communication, and cable television signals. Due to much lower attenuation and interference, optical fiber has large advantages over existing copper wire in long distance and high demand applications. Today, our communication has improved to such a great extent thanks to optical fiber communication. So basically, sir, it is an informative session for us, for all our faculty members, and we would be sharing our the thoughts with our students related to this session, and expecting a good session from NITRR. we have been in the past associated with NITRR. We have participated in around 12 events. So basically, this is our 13th event, and we thank NITRR and Dr. Chaudhary for this event.
Thank you for introduction and being interested in the ICT based program of this institute, and I hope we will have good interaction in the coming session for this program.
Right, sir. Thank you.
We move to the next center, Northern India Engineering College, New Delhi. Northern India Engineering College, New Delhi. I invite local coordinator Mr. Ankur Sood to introduce about the center. Mr. Ankur Sood.
Yeah, good morning, sir.
Good morning.
We have organized this FDP program, and we are having total around 20 members right now. Due to examination, some members, more member will be added in the coming days. So Mr. Dr. Rajiv Sharma, he has organized this event, so he will be speaking next.
Good morning, sir. I'm Professor Dr. Rajiv Sharma.
Good morning and welcome, Dr. Sharma.
I'm
a few words about the program.
Department, and we've been associated with this kind of programs with the NITTR over a number of years. Recently, in the month of September, we were a part of a program with the name Optical Fiber Communication Technologies. Now again, since this program is head in this context, it is advances in optical fiber communication technologies. So I'm looking forward that, as it has always been, that the faculty has been benefited learning through this distance learning programs. And also now I invite our principal sir, director sir, Professor Dr. G.P. Govil. He's also here. Now I'll request him to say a few words in this context.
Good morning, Professor Chaudhary. How are you? Yeah, I would like to thank Professor Punia and yourself, who has taken a lot of initiative to run this program. Actually, we are the nodal center over here, and we have been conducting it very regularly. And these types of programs are really very, useful for our faculty to first of all motivate them and to know about the technologies in the subject actually. And OFC is the one which is coming up very well for the communication part of it, and which will go a long way. I would like to suggest one thing more. You must have a project session over here, in the sense, after this culmination, from your side or from your faculty side, a project form should come, and all the colleges should write a project on that and then come back to you. Then it will be much more meaningful than otherwise, because it is just listening is a one-way traffic. Of course, it is a communication either way, but it's a learning process only that the faculty will listen. But if the faculty is being given in the form of some project, then it will be much better and much more meaningful.
Okay. We will see to it.
Yeah. Thank you. Thanks a lot.
Thank you, sir, and thank you for the introduction and your interest in the programs of this institute. And now we move to the next center. That is the City Institute of Engineering, Jalandhar. City Institute of Engineering, Jalandhar. May I request local coordinator Ms. Pooja Rana to introduce about the center. City Institute of Engineering, Jalandhar.
माइक ऑन कर लीजिए मैम.
You switch on your mic. I invite Ms. Pooja Rana to say few words about their center. That you are audible.
Hello.
Hello.
Good morning, sir.
Good morning, ma'am.
Good morning. I am from City Group of Institution. My name is Pooja Rana.
Okay.
And we are very, very excited about this program. This is the very informative program, and I know all the faculty will get lots of things from it. And due to examination today, we have a less number of faculty, but within 10-15 minutes, the whole number of faculty will be here. So we are very thankful to you for providing this particular environment to us. Thank you so much, sir.
Okay, thank you, and stay connected.
Sorry, sir.
Thank you.
Yes. Okay, sir. Have a good day.
Definitely, I hope link will improve and more participants will join.
Yes, sir. Definitely, definitely. There will be we will within 1 hour the number of participants definitely will increase, and we will get a lot of things from this particular FTP program.
Okay. So we will start the session, another session after the tea break. Maybe after 10-15 minutes, we will again come to you. Thank you. So thank you all the local coordinators at different nodal centers for introducing about their institutions, and I hope this audio video connectivity will not be the problem for all these centers, and we will have good interaction in the coming sessions. Now there will be a tea break for 15 minutes, and I request all the nodal centers to be here at around 11:20. So after 15 minutes, we will start the session around 11:20. So thank you, and hope we will be there at after 15 minutes. ये आपका आ गया चाय वाला
तो क्लास लग रहा है, मैं उसको भी करूं जल्दी।
सही हो गया कनेक्टेड अरे सो So good morning. Good morning all the participants at different nodal centers and participants in the studio. So I hope everybody enjoy the tea. And now we are starting with the first session of the program, that is fiber optics communication technology. So am I audible at all the centers? I request all the participants to be seated so that we can start the session.
SRM College of Engineering. Yeah, please reply, sir.
देखो से
Global Institute of Global Institute of Technology, Amritsar.
I'm audible at your place. Global Institute of.
Yes, sir. Yes, audible.
I'm audible at your place, ma'am.
Yes, sir.
Okay, thank you. And we will start the session, next session now. So I will start with the session, first session on fiber optic communication technology. I will give overview of this, the optical fiber communication in this program as per our dual time frame. In this session, I will discuss about what is the fiber optic technology, why, what, and how fiber optic technology is fulfilling the need of the communication, why we need optical fibers, and what are the different OFC systems present and in future which will come as the communication part of communication technology. So I hope everybody is now familiar with the communication. Communication is the need of the hour. I mentioned it was the need of the hour, and it is the need of the hour, and it will be the need of the hours. And during the past, many developments has been taken place in the area of communication. It started, say, from 1896 with the very communication at very low level, and now today we have a communication system where everything is included. It is not now today the voice which is important, but now our telephone, our instrument, our telephone set, it has all type of information, all type of communications are possible with these systems. And we generally know it is the exchange of information, and mostly these communications are required for telecommunication. Our telecommunication departments, telecommunication ministry, they are looking for all these communication issues. So when it is the exchange of information over the long distance, so we need a communication system. And generally a communication system, it comprises of transmitter and a receiver, and they are connected by a link. And this link may be in any form. It may be radio link, it may be microwave link, it may be any other link. So we have some sort of information, and we want to transmit this information to distant place, and so we need a communication system. Our voice cannot go to long distance, so this requirement is fulfilled by the communication system. And generally we have three types. In the present scenario, we have three type of information that to be exchanged: voice, video, and data. Some 30 or 40 years before, it was the voice which was there. There were very few telecommunication telephone systems, but now with the development of technology, with the development of requirements or need of the society, now video and data, they are also the part of the communication. Our telecommunication system, they are providing all the different type of services by transmitting voice, video, and data, and the information is often carried by the electromagnetic carriers. Our communication system, they are based on the electromagnetic carriers, and the frequency ranges from few kilohertz to megahertz and terahertz. So depending upon the frequency, the capacity or the strength of the system will depend upon what is the carrier. So we started with the radio wave system where the frequency was of the kilohertz. Then we moved to the microwave communication where the bandwidth was of the order of megahertz. Then now we have the terahertz frequency or 100 gigahertz frequency or more than that. So the main parameter in communication system is the bandwidth. And bandwidth, it decides how much information can be carried out by the system, or what is we call as the capacity. What is the capacity of the system? And that depends upon the bandwidth. Sorry. ये मिश्रे नीचे लाता रहेगा मेरे इसमें स्टॉप शेयरिंग वाली एक लाइन आती है मेरे हाइड कर दूं मैंने कहा कोई ये बात ओके so they are the frequency, they range from maybe from kilohertz to megahertz and terahertz range. So all they are the electromagnetic waves or electromagnetic frequencies. So they are all the carriers. So any communication system generally comprises of what we have. We want to send some information, and this information, mostly the information we want to send is not in the electrical form. So we have to convert this information into the electrical form. It may be in the analog form or in the digital form. So information source, which is a electrical signal derived from a message signal. So it may be sound, video, and data, or what we call as the multimedia. So then we have a transmitter. The role of transmitter is to modulate the signal. Because the signal cannot travel, I need a carrier. Now this information is superimposed over the carrier or loaded over the carrier, but is called the modulation or modulating the carrier. So this is generally an electronic module which converts a signal into suitable form for propagation over the transmission medium. So we call it the modulator or modulating the carrier. So a transmitter is required to modulate the carrier, and it comprises of different electronic components and maybe some source of carrier. And so this source of carrier, it can be radio wave transmitter, it can be microwave transmitter, and nowadays it can be an optical transmitter. So transmitter part, then we have a transmission medium. So from the transmitter, the information is passed on to the transmission medium, which carry the information to long distance. So from the source to the destination, there is a transmission medium, and this transmission medium is a medium suitable to carry the information or to carry the modulated wave. So it may be a pair of wires like copper cable or a coaxial cable, or it can be a radio link, free space. So radio wave, they can travel in the free space. They have a long wavelength and they can travel long distance. As a result, it can be free space also. So the signal is transmitted over the transmission medium, and ultimately it reaches the receiver. So we call it as the transmission medium or channel. So at the receiver, again, the signal is accepted there, and now the signal is depending upon the quality of the signal, it may be amplified so that it can be here again the information has to be separated from the carrier. We call this process as the demodulation. So demodulation takes place there. So whatever signal information we were sent, now the information is received at the receiver end. Now this information is passed on to the user, or it goes to the destination. So this is what we have any communication system where we have a transmitter or we have the receiver part. So these can be electronic transmitter, or it may be any other form of a transmitter and the receiver. Both they are in the same form. So if we look at the telecom system in 70s, mostly I mentioned the transmission mediums, they were either the twisted pair, copper wires or metallic wires, there may be coaxial cable or radio wave or microwave as the carriers, and sometimes we use the satellite also. Now these satellites, they are used for the transatlantic links or in global communication. So the signal can be, communication can be through satellite. Many satellites, they are the communication satellites. So they are also part of the system. And generally the signal type are either in the analog form or in the digital form. So any type of signal can be there, and our communication system, they are mostly transparent to type of the signal, and specifically the modern communication system. So we can have the analog signal, but mostly our communication is in the digital form, because you know the digital form, it is a more secure and more reliable and more you can say more accurate as compared to the analog part, because either the information will be there or not there. The noise in digital signal will be very less as compared to the analog signal. So mostly we have the digital communication, but some system we have the analog is also there. And all these systems, they have what we call as the high attenuation. There are two parameters in the communication. One is the attenuation, other is the bandwidth. We want attenuation to be as small as possible, so that I should reach at the longest possible distance. So long haul link, small attenuation, and bandwidth. We need large bandwidth. So bandwidth means capacity. So I need a high capacity system. And this bandwidth, it depends upon the pulse broadening. So we know in all the system, there is a broadening of the pulse. When the signal travels, there is a broadening of the pulse. And broadening of the pulse, it will limit the bandwidth. So it is inversely proportional to the broadening. So we want this broadening to be as small as possible. So both attenuation and pulse broadening, they had to be very small. So as a the earlier system, they were having these limitations: attenuation limitation and bandwidth limitation. The attenuation, if we look at the attenuation, generally it is measured in dB per kilometer, decibel per kilometer. If you look at any copper system, the attenuation is the order of 15 to 20 dB per kilometer. A large attenuation. So as a result, we need the amplifier maybe after 3 or 4 kilometers. Similarly, the bandwidth, the available bandwidth, if we use these radio and microwave frequencies, it is in the range of kilohertz to megahertz. So they are not very wide bandwidth. So they cannot carry large information. All type of information cannot be put over these systems. So there were limitation of the system. Both they were attenuation and bandwidth limited system. So as a result, we need a system where the attenuation is small and where the bandwidth is more. So then comes the fiber optics technology. It is also called light wave technology, or in general, it is also called photonics technology. It is the photonics. Like in electrical or electronics, these are the electrons which moves. But here, these are the photons which move. It is the movement of photons. The information is carried by the photons. And in this technology, it uses the light as the primary medium to carry the information. So instead of radio and microwaves, your carrier is a light wave or optical wave. So it carries optical wave or light wave, it carries the information, and light is often guided through the optical fiber. So it is a point-to-point link, like our copper or microwave cables, we have the optical fibers. So the transmission channel is the optical fiber, and most of the application, now our optical communication, it is developed in the infrared, using the infrared light or invisible light. Although the system started with the visible part, the first system they were tested with the helium neon laser, which is in the visible part, but later on the system moved to the infrared frequency because of the attenuation limitations. So I will come to that part, because if you go to the infrared, they are the higher wavelength or lower frequency as compared to visible part. We talk about the optical frequencies, and in the optical frequency we have the IR, we have visible, we have the UV light. So although working in the IR region, you will get less bandwidth, but loss will be also small. So in any communication system, my approach is, first I should reach at the destination. So first parameter is the attenuation parameter. Second parameter is the bandwidth parameter. Whenever in any system, first we check the attenuation, then we go for the bandwidth. So first I should reach there, then I will analyze what is the data rate. So because of this limitation, the system were working at the IR region, but here we also get very large bandwidth as compared to the existing system. So these technologies provide what we call as almost near zero loss and near infinite bandwidth. Losses are very, very small. So I will mention in our copper cable, losses are around 20 dB per kilometer. Whereas in optical fiber communication, the losses are 0.2 dB per kilometer. So around 100 times more benefit. So attenuation is reduced by the 100 times. So the system can go a long distance as compared to our copper and microwave. Similarly, large bandwidth. Here we do the frequency. So the bandwidth is also in the terahertz. So terabits of data is also possible. So they provide a huge bandwidth and very, very low loss. So as a result, this is a modern optical fiber communication system. So we will see we have the same information, we have the same transmitter where we have the electrical transmitter, but here we have the optical source. So after the electrical transmit, one put a optical source, and this source is convert the electrical signal to optical signal. The sources are either our LEDs or we have the laser diode. So what we call it the photodiodes. So they convert electrical signal to optical signal. So we have the optical signal here. Now this optical signal is transmitted over the optical fiber. The optical fiber, it carry the optical signal and ultimately it reaches at the destination where we have the optical detector. Now optical detector, it receives the optical signal and then again it will convert this signal, optical signal to the electrical signal. So ultimately again we have the electrical signal. So a optical communication, it is something between the existing system. Earlier we have the electrical input, we have the electrical output, but in between the signal transmitted was the electrical signal. To overcome the attenuation part, now we have converted the electrical signal to optical signal. Now this optical signal, it travels. Now this optical, here the optical carrier, it has huge bandwidth and very, very low attenuation. So here again, same part. So optical communication, basically it deals with the optical source, optical fiber and optical detector. These are some components which were introduced in the existing system, and it is the same system which is working in a different fashion. So transmitter here, the electrical signal is converted into optical signal. Using some optical source, we may call it as the optical modulation. The modulation is the optical modulation. We have the electrical data, we have the optical carrier, and they are the modulator. So this modulation, it can be the direct modulation or it can be indirect modulation. We will discuss more in detail. Then transmission medium is the optical fiber. The optical signal is transmitted through the optical fiber to the receiver. Now instead of the copper or coaxial cable, we have the optical fiber, and at the receiver again the optical signal is reconverted to the electrical signal. So a user, he always receives the electrical signal. So there is this process, there is a demodulation at the receiver section, and ultimately again we have the electrical receive, which is now given to at the destination. So our telephone set, it will receive the electrical signal. So it is the same system, but at the intermediate and in between, we have converted the electrical signal to optical signal, and again the optical signal to electrical signal. So it makes our communication system more effective, high capacity system, and more efficient system. So why need optical technology? I mentioned, if you look at last say 3 to 4 decades, you see there are the remarkable and dramatic changes in electrical communication system. Our requirement was only the voice communication. If you look at the system in 70s or 80s, the only requirement was the voice communication. So there was a telephone, very few telephone, say in a village or in a city. But nowadays, you see the number of telephones. our communication requirements needs has increased in a manifold. So as a result, there is a now increase in data. The information is not only the voice, but now there is a phenomenal increase in voice, video, data, and video communication. Our information is not only the single information. Now there are many things which have been added to this the information part. This is what we have, the different technologies. So as a result, now when our data has increased, we need demand a system of larger capacity, more data, more capacity now, and more economical communication system also. So larger capacity. Now if you look at the voice and look at the video, a video generally it need almost 4 times more bandwidth as a voice signal. We know in our communication. So all multimedia, they need huge bandwidth. It's not possible with on the copper cable. So we need a system with larger capacity and even more economical system also. Nowadays, different telecom company service providers are there in the market. No company can increase the call rate. It is a very competitive market. So as a result, one have to look for the economy also. The system has to be very fast also. So as a result, looking at all these requirements, the lightweight technology, which is the technological route for achieving this goal. It is a most cost-effective way to move huge amount of information quickly and reliably. We want the system to be very reliable. System should be workable at all the time. Otherwise, the company they will be fined. Now we have the many issues like call dropout. Many companies are facing all these problems. The system has to be very reliable and very fast also. We don't want raw stale information. We want information to be very quickly and very fresh information. What is happening in the world, we want to know. So that the information can be received at a later stage. So nowadays, we know that world now it has become a global village, and everybody wants what is happening anywhere in the world. So as a result, the data has to be very quick and very reliable. And we know the fastest speed possible is with the photons. Photons can travel with the fastest speed. That's why photonics. So photonics can provide a solution for this ever increasing demand. So optical transmission, I mentioned, we want more and more capacity. We are not happy, but we have. Ye dil mange more. So more capacity, more and more capacity. As a result, there is a technical revolution in the communication industry for large capacity, high quality and economical system at global level. It is not the telecommunication is not only at the country level or at the national level, it is an international communication system. The world is connected through a communication link all over the globe. So as a result, so if we look at the existing system, earlier system, if we want to fulfill this requirement, we have the radio waves, we have the terrestrial microwave systems. So which were the, you can say, the communication started with these systems, and they have long reached their capacity. You cannot add more to these systems. They are already fully occupied. So as a result, these systems cannot fulfill this requirement of increased capacity. And then we also mentioned global requirement. So radio waves and microwave, they cannot not go to long distance. They can cover maybe few kilometers. But at the global level, distances are very large. Thousands of kilometers are there. So as a result, that requirement was fulfilled by, to some extent, by satellite communication. The satellite communication comes into existence. We have the geostationary satellites, and those satellites, they are used for the communication. So all these satellites, you see, they are based on the microwave frequency. They have uplink and they have downlink. They are all geostationary satellites and synchronized in such a way so that we get the information. But if we look at the provision of the satellite communication, they can they cannot fulfill this ever increasing demand. One point is, it is extremely high initial cost of launching. Satellite, they are very, very expensive, and cost of launching is very, very high. Every country cannot afford to launching the satellite. So very, very expensive. So we cannot talk about the economy here. Geometry of suitable orbits. So a satellite has to be placed in an orbit, in the space. Already there are a number of satellites in the space. Many times we heard in the news that there is already congestion in the space, and as a result, international bodies are there where to put the satellite in space. One have to go for the international bodies to put the satellite in a particular orbit. So as a result, there is again a requirement for the suitable orbit. Then available microwave frequencies. I already mentioned that microwave, they have already reached their capacity. So you cannot add more to microwave channels. And for satellite, you need not on the one frequency, but two frequencies. You have uplink, we have downlink. So as a result, more microwave frequencies are required for satellite communication, which are not available.
But sir, you say these frequencies are not available or not possible to send for a long distance.
Yeah.
How we can transmit the data? Because
That's why we are moving to optical fiber communication.
then what would be the light source for this communication system?
I'm coming to that. Light source. We will come to that. So light sources we need. Mostly these are LED or lasers. So we need the light sources. My point is that microwaves cannot fulfill the requirement. Microwave frequency cannot fulfill the global need of the communication. As a result, we have to go to the optical frequencies. So microwave frequencies are not available. More microwave frequencies are not available. And then if needed, repair is nearly impossible. It is not feasible or practically possible to repair a satellite. So whenever there is some problem with the satellite, it can be from the ground station, it can be oriented in such a way so that it can fall in some ocean. So as a result, repair is very, very difficult or nearly impossible. So the next option is the optical frequency. So optical communication. So we know the radio and microwave, they are not able to fulfill the need. As a result, there is no option. We have to choose some electromagnetic wave from the electromagnetic spectrum. So if you look at the electromagnetic ladder, so after microwave, there comes the optical frequency. So to see more and more, we have to climb up the ladder. So optical communication, optical frequency is the solution. So we move to the optical frequency. So in the all your carriers are from electromagnetic spectrum. So earlier we were having the radio wave communication. We are having microwave communication, which were already very, very congested. Adding more to these is not practically feasible. So as a result, we go to the optical frequencies. So optical frequencies are mostly in the region of infrared, visible, and ultraviolet. They are all the optical region, optical range. So we have to choose some frequency from this region. So, and here the frequency is in the range of terahertz. If you look at the radio waves, they are a kilohertz. So bandwidth available will be in the kilohertz only. Similarly, microwaves, they are in the megahertz or few gigahertz. So as a result, the bandwidth will be few gigahertz, somewhat more, but even limited to gigahertz frequency only. But if you move to the optical frequency, the bandwidth will be in the terahertz. Terahertz is 10 to the power 12. Very, very large frequencies are available. So they will provide the huge bandwidth. So the optical communication, they work in the optical region. So they provide huge bandwidth. So if you look at again the justification for that, if you look at any system, how the optical transmission fulfills its need, you will see from this slide, the information carrying capacity of our communication system is directly proportional to bandwidth. So if you look at this relation, this is the well-known Shannon-Hartley theorem in communication. The capacity is proportional to bandwidth and then into log 1 plus signal to noise ratio. So now in order to enhance the capacity, we have the two parameters. One is the signal to noise ratio, other is the bandwidth. So here we can improve the signal to noise ratio and we can increase the bandwidth. But the signal to noise ratio is in the logarithmic form. So if you increase the signal to noise ratio by 10 times, the net effect will be 1 time. Log 10 is 1. But any increase in bandwidth, it will directly enhance the capacity. So best option is let us increase the bandwidth. And so wider the bandwidth, greater is the information carrying capacity of the system. And in communication, there is a thumb rule that bandwidth is 10% of the carrier frequency. So whatever you carrier choose the carrier frequency, it is theoretically around 10% of that. So the table will show you if you have any system working on the radio wave system. So let us working at very high frequency radio waves at around 100 megahertz. Your bandwidth will be 10 megahertz. Microwave frequency at 10 gigahertz. Your bandwidth will be around 1 gigahertz. And light wave system, which is around 10 to power 15 hertz or 10 to power 6 gigahertz. So around 10 to power 14 to 10 to power 15 hertz. So here the bandwidth will be 10 to power 5 gigahertz. So you see, if you compare it with the microwave frequency, it is 10 raised to power 5 gigahertz, or it is around 100,000 times more that can be achievable with the microwave frequency. So it is a excessive bandwidth or huge bandwidth which is sufficient to fulfill the need of the present communication or that of the foreseeable future. So it's a huge bandwidth, and generally we call it as a infinite bandwidth. So communication system with light as a carrier, it has a great potential, and as a result, great deal of attention for development of the system in the past decades. So we have the communication system which can fulfill the global need of the communication industry. So generally, if you compare our normal communication channel capacity of the telephones or system which are existing, if we have a copper cable system based on the copper cable, the bandwidth is around 100 kilohertz, and you can put around 2000 telephones on a single pair. Normally in communication, we have the trans and we have a receive. It is always in the pair. So you can put around 2000 telephones on one pair. Similarly, if we have a coaxial cable, around 30,000 telephones can be put over the pair. So if your need is more, we have to add more and more pair. That's why we have 100 pair, we have the 400 pair, we have the 1000 pair. More and pair are added to the cables, so they become more and more bulky cables. In case of optical fiber, the bandwidth is around 90 terahertz. So we can put more than 3 lakhs telephone on a single optical fiber pair, or more than 90,000 video signals can be put over the optical fiber. So it has a huge potential and huge capacity. So optical communication systems have lot of benefits, lot of potential for communication industry or for fulfill the need of the communication requirements. But there are the difficulties. It is not that it is so easy. There is a potential, but we know there are the difficulties. The major difficulty is transmission of light wave over any useful distance is through atmosphere is impractical. You cannot send light to long distance because they are the short wavelengths. So as a result, there is a high attenuation and absorption of ultra high light frequency by water vapors, by oxygen, by air particulates, because these are short wavelengths. And in the atmosphere, there are a large number of small particles or micron-sized particles. If you look at the wavelength of light, it is of the micron order, maybe 0.8 micron, 1.3 micron. So around 1 micron is the wavelength of light wave frequencies. And if you look in the atmosphere, you will find large number of micron-sized particles. And we know the diffraction. Diffraction will be prominent only if the wavelength of light matches with the particle size. So there is a large diffraction, or what you call different type of scatterings. So as a result, the light undergoes scattering, it undergoes diffraction, so it will not reach at the destination. So as a result, only the practical way is to use a fiber guide, to use a light guide. So I need a guiding medium like our copper or coaxial cable. I need a optical fiber cable. So optical fiber guide is required for practical optical fiber communication. So we need a optical fiber, and this fiber generally it comprises of a medium. The light can travel in a transparent medium. So I need a transparent medium. So a optical fiber, it is a strand of glass or plastic material. The glass is a transparent material, or nowadays high quality plastics, they are also transparent to light. So as a result, they are the glass and plastic material with special optical properties which enable light to travel a large distance down its length. So the signal should be able to travel through the optical fiber, and this fiber should have high order of transparency. More transparent is the glass, more is the distance possible. So these are the fiber with very, very high quality of high optical property, so that signal can travel long distance. So mostly these fiber, they comprises of core and cladding. So it is a cladded fiber. It is a concentric layer where you have a core and cladding. So both they are basically constitute an optical fiber, and light travel in the optical fiber through the core by total internal reflection. So we will discuss it in more detail. The total internal reflection is the basic phenomena for propagation of light, and we need the cladding also. The cladding, if there is no cladding, you see there is a loss at the interface. So cladding, it helps for efficient total internal reflection. So if the cladding is there, the propagation will be more efficient. Otherwise, there will be a loss of the signal at the interface. But if there is a cladding, the loss will be very, very small. So core plays a many roles in the optical fiber, but in nutshell, a optical fiber, it comprises of core and cladding. So these are the part of our communication of optical fiber or practical optical fiber for guiding of light. So the solution for long distance communication is the optical fiber. But another point is light source. We need a intense light source. The light sources were not available. If you look in the earlier era or very ancient time, optical communication or optical signals were there. The fire is a source of optical signal, and many a time these were used to communicate, specifically in the far distant or inaccessible distance, in the forest. Our army troops, they used to ignite the fire just to send the message, communicate that we have reached at this place. So we have the optical source of fire, or we have the incandescent lamps, we have fluorescent tubes, or we have the xenon lamps, powerful lamps also, but they were not very, very intense. We need a very, 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 very small source, very, very narrow source, highly intense source, or coherent source. The light, when it travels, it has different phenomena. The one phenomena is the interference. So light wave, they undergo interference, and for interference, coherent is a basic condition. So I need a very, very high intense source which is coherent also. So the light sources which came with the laser. So invention of laser in 1960, and then optical fiber waveguides in 1970. So optical fiber waveguide which were available before 1970s, they were having very, very high attenuation. The attenuation was of the range of 1000 dB per kilometer, because these were not very, very fine optical fiber. Normal glass, the attenuation is more. It cannot carry light to long distance. So as a result, the optical fiber with low loss, they were developed in 1970, around 20 dB per kilometer. Optical fiber, they were developed. Now the 20 dB per kilometer, they were losses are comparable to coaxial cable or copper cable. So then you can propose, you can utilize this material where the losses are either comparable or lesser. You cannot propose any medium where the losses are more. Nobody will accept your proposal. So as a result, the optical fiber, they were developed, the invention of laser in 1960 and high quality optical fiber waveguide in 1970s. It provided an edge toward making the dream of carrying huge amount of information a reality. So it is the laser which plays a very, very important role in development of optical fiber communication. So a laser, it has revolutionized the optical communication area. Optical communication system were there also, but not in a high capacity. But with the laser, and then of course optical waveguide, they were developed, and they happen to be the basic component for a communication system. So as a result, the optical communication system, they achieved a great attention with the availability of lasers. So this is the fiber optic timeline, how the system developed. Just giving you the brief historical development of the system. If you see, even the optical fiber, they were used as for scanning and transmitting television images in the recent in the past development, but these were the uncoated fiber. In physics, we all know we have the scintillation counters or sodium iodide detectors. With these detectors, they are coupled to photomultiplier tubes, and in the scintillation, it is the light which is produced. The light, it fall on the photocathode of the photomultiplier tube. Now that light, it was guided by the optical fiber, but in that case the distance was very small. It was a small optical fiber, so it is not a long distance. So as a result, one used the uncoated fiber. They were used for many applications, but in 1950s, the light transmission through bundle of fibers, because these are the coherent bundles, they were used for development of flexible fiber scopes, which were the requirement in the medical field. So in the fiber optics or optical fiber, they were developed or they were searched for application in the medical field. And still in the medical field, the distances are not large. Hardly the fiber optics, fiber cable, they were used to send the light to just to look inside the body, just like the endoscope or fiber scopes. Earlier, they were the rigid fiber scopes, but with the development of the optical fiber, availability of optical fiber, now they are the flexible fiber scope. It is just like a plastic pipe which can be moved in any direction. So flexible fiber scope, and the first fiber optic endoscope, it was tested on the patient. In this area, the person who worked on this area, it was again the Indian scientist N.S. Kapani. He is also known as father of fiber optics, who was working in these areas. So as a result, but his interest was toward the medical application. So first endoscopes were developed in 1957. Then invention of laser in 1960 by T. Maiman. So lasers were practically available in 60s, and in 1960, Charles Kao, a Chinese scientist, he was again working in the lab in Dr. Kapani's group, and he proposed that cladded fiber cable with lower losses can be used as a communication medium. This is what he proposed. If we can reduce the losses in the optical fiber cable, it can be used as a communication media, because the optical fiber, it works on the optical frequency and it can provide a huge bandwidth. So bandwidth is there, optical frequency are there in the electromagnetic spectrum. But if we can reduce the losses of optical fiber, it can be used as a communication media. And Corning Glass Company, we know all our glasses, they are made by Corning. So Corning Glass Company in US, they took up this challenge and they come out with the optical fiber with losses below 20 dB per kilometer. Now the losses are compared to existing copper cable, so that put a foot forward in development of the optical communication system. Then another requirement in the communication is the semiconductor diode lasers. Now the requirement is I should be able to modulate the source, and I should be able to couple the source to optical fiber. You will see when I talk about the fiber. So directly it comes that it is very, very small, very, very thin in diameter. Now I need a very, very small source. if you you remember the semiconductor laser, they were developed in even 1962. But those semiconductor lasers, they were very bulky. They were not very narrow. But and they were giving to the constant input. There was no input. So for modulation requirement, I need an input signal, which can be modulated. So these semiconductor lasers, they are the diode laser, and diode laser, they are very small in size, and they have some input current. So basically, they are called injection laser diode, ILDs. So it is the injection current which is important for the communication point of view. I can modulate this current. I can superimpose my signal over this current, and this current is provided to the source. So if I modulate the input current, the output of the source will be modulated. What is the modulation? It is the change. It is the change from low to high value. So your light will be low, your light will be high. So it is modulation. So semiconductor laser, they were developed in around 72, and so we get the semiconductor diode laser, and in 77 the first telecom links, they were tested by GTE in Los Angeles and AT&T in Chicago around same time. So now it is a GE company. So they send the live telephone signals through fiber optics or through optical fiber. So at that time they used 850 nanometer, again, which is maybe on the far end of the optical frequency, or maybe on the near end of the IR frequency. So our bands, they are not very narrow. They are all the band, overlapping band. So the window which was used is 850 nanometer, and the losses were around 4 dB per kilometer. So 4 dB per kilometer, if you look at the copper, 20 dB per kilometer, so 5 times less attenuation, means you can achieve 5 times more distance. Then the fiber which was used was the multi-mode fiber. We will come across, we have the single mode fiber, we have the multi-mode fibers. So they are basically beneficial over the in terms of the broadening of the pulse. So multi-mode fiber, they have more dispersion. Single mode fiber, they have less dispersion. But initially the multi-mode fiber was used, and another parameter is the 9 kilometer. It is the repeater distance. So if your signal is attenuated, after certain distance, it have to be amplified. So we call it as the repeater. So a repeater, it repeats the signal after certain distance. So in generally in the copper system or coaxial cable, the repeater spacing is around 3 kilometer. So after 3 kilometer, we have to put the amplifier. And amplifier, it is again a high cost component. So but here the amplifier was required after 9 kilometers. So again, it is a 1/3 reduction in the number of amplifier. So naturally you need lesser number of amplifier, so the system cost will also reduce. So it was the first bird fiber optic link which was tested in 1977. And of course, any system, there are further improvements. There were improvement in the optical sources. There were improvement in the optical fiber. There were improvement in the electronic systems as well. So as a result, we have the second generation systems. So in 80s, we have second generation systems where the wavelength shifted from 850 nanometer to 1310 nanometer. Why it shifted? I mentioned it was because of the loss, attenuation. And in light, I mentioned the major loss is the scattering loss. And in optical communication, we see the major type of scattering is the Rayleigh scattering. And if you know, the Rayleigh scattering is inversely proportional to 1/λ4, fourth power of wavelength. And if the wavelength is more, scattering will be less. So while by shifting from 850 nanometer to 1310 nanometer, the loss is reduced from 4 dB to 0.5 dB per kilometer. The only point is that I need a source. I need a semiconductor optical source at 1310 nanometer. So there is a parallel development in the optical source, optical fiber, and optical detectors. So optical sources, they were made available for 1310 nanometer window, and then multi-mode fiber, they were replaced with a single mode fiber. You will see the single mode fiber, they are smaller in diameter, around 10 micron size, whereas the multi-mode fiber, they were around 50 micron size. Earlier 62.5 micron, then 50 micron. So we use the multi-mode fiber, single mode fiber for the communication point of view. If you have a multi-mode fiber, we have two type of dispersion, two type of broadening mechanism. One is the intermodal dispersion. Number of mode are traveling, there is a dispersion because of the path difference. Different mode, they follow different path and they reach at different time. That lead to broadening of the pulse. So the solution is go for the single mode. So there are only one mode, so no intermodal dispersion. So single mode, if they provide high data rate, so as a result, the losses are 0.5 dB per kilometer. The data rate is more than the existing multimode fiber. Then, but here, how the amplification, how to amplify the signal. Normally, in the earlier system, the optical signal was converted to electrical signal and one used the electronic amplifier. Again, the amplified electronic signal is converted to optical signal. So when you convert from optical to electrical, electrical to optical, there may be the loss of the signal. And there are many number of amplifiers. Number of repeaters are there after certain distance. After every 3 kilometers or after every 9 kilometers, they are the repeaters. So at the end, there may be huge loss of information, huge loss of data. So this was you see, the bottleneck in the 1310 nanometer system, because in this window, optical amplifier were not available at that time. So then comes the third generation systems. So in the third generation systems, the wavelength shifted from 1310 to 1550 nanometer. Now 1550 nanometer sources were made available. And for your information, these sources are not our direct semiconductors. They are not silicon and germanium. They are basically they are direct semiconductor alloys. Gallium arsenide, gallium indium phosphide. So basically, different alloys are made. So if you look at the 850 nanometer, the first sources they were gallium arsenide. Then these are the binary alloys, and these are the ternary alloys. We have the quaternary alloys. 1550 sources, they are the quaternary alloys. You have to add 4 alloys, and you know, when alloys they are mixed in such a manner so that the basic lattice structure should not disturb. So it was not easy, but thanks to researchers, they provide the 1550 nanometer source. Then we have the single mode fiber, where the losses is around 0.2 dB per kilometer, and these losses are basically our Rayleigh loss. If you calculate 1 over lambda 4 at 1550 nanometer, the loss comes out to be 0.2 dB per kilometer. Then comes the amplifier. It is the EDFA, erbium doped fiber amplifier. It is an optical amplifier. So it amplifies the signal in the optical domain. So there is no need to convert optical signal to electrical signal. So as a result, it provides a major, you can say, solution for the amplification of the signal. But EDFA, it works only in the 1550 nanometer range. This is an amplifier which works at 1550 nanometer region, or very, very promising amplifier. We have no amplifier with that much benefit in the 1310 nanometer. Either we have the semiconductor amplifier or we have the Raman amplifier, which are not as efficient as our EDFA. And another point is, this EDFA is on the fiber itself. It is also called fiber laser. A fiber laser giving output at 1550 nanometer. So EDFA can be developed over the optical fiber. Certain region of optical fiber is domed with the erbium. So it acts as a lasing medium. So we will discuss more in detail on EDFA. Dr. Tawadi, he will cover this part. So here with these systems, they can give you data rate in the range of gigabits per second. So we have the third generation system. Now in further developments, the developments are to how to enhance the data rates, how to get more and more data rates, how to go from gigabits to terabits of the system. So system comes in 90s, in 93, Bell Lab, they were able to send 10 billion bits per second through 20,000 kilometers of the fiber without using any repeater, but using WDM system and soliton pulses. Soliton pulses, basically we call these are the non-dispersive pulses. These are the special type of pulses which are non-dispersive. So they will not disperse. As a result, they can give you high data rate. We will discuss more in detail when we will discuss the non-linear effects. These are basically non-linear pulses. So then in 1966, these NTT and Bell Lab, they were able to send trillion bits per second over the optical fiber. So the further improvements are to send more and more data rate. It is similar to analogy of computers. If you look at the computers, the basic system is your CPU, your input-output device, and your memory. It is the same system after more than 70 years. So we are improving the speed of CPU. We are enhancing the memories. We are putting more and more input-output devices at the interface. So now the requirement is how to achieve the terabits of data. Still, we are not able to send the terabits of data commercially. At laboratory, these has been tested, but commercial system, they are either operating at maybe 10 Gbps, 40 Gbps, or maybe maximum up to 100 Gbps, not terabits per second. And we know the optical fiber, optical frequency, they have potential for terahertz or terabits of data. The only limitation is the electronics part. Electronics cannot operate at such a high speed, or electronic pulses. If you are talking terabits of pulses, you need the picosecond of pulses. You need large number of pulses per second. So as a result, electronics is a hurdle between the high speed. So we need what we call the all optical network. Everything have to be optical, or everything has to be over the optical fiber, so that there should be minimum coupling loss. So our coupling devices, because you need the different components. You need the optical source, you need the optical detector, you need the connector, you need the coupler. So many components, optical components are required, and they have to be of the same dimensions if we want the efficient coupling. If the components are of different size, the coupling cannot be efficient. There is a loss of power. So as a result, to fulfill the terabits requirement of data, we need the optical sources. So as a result, I mentioned the Charles Coe, he proposed that optical fiber can be used as a communication medium. So he was awarded Nobel Prize in Physics 2009 for proposing this groundbreaking achievement of optical fiber communication. So the person who worked on the optical fiber in 1966, he proposed optical communication fiber as a communication media and won the Nobel Prize in 2009. I will just show you, and these are the two persons who share this Nobel Prize on developing or some CCD sensors. So optical communication get recognition at the Nobel by the Nobel Society in terms of the telecommunication. So I will show you a small video where
this remarkable video from the February 1966 shows Charles Coe, the pioneer of optical fiber communication, working in the laboratory. It shows him experimenting with a prototype hair-thin optical fiber made of glass. He was part of the British team that first proposed that huge quantities of information might be carried over vast distances by this novel means. This was only the beginning. The transmission loss of these early fibers was so great that many argued that Charles's vision was doomed to failure. However, later that year, Charles and George Hockham published the defining paper, which revealed that none of the current imperfections were fundamental. Here is the helium neon gas laser, invented just a few years earlier, which provided a sufficiently bright light to launch into the incredibly tiny core of the single-mode fiber. The intensity of the laser light was modulated, and that information traveled along the fiber as pulses of light, which were converted back to an electrical signal at the far end. All this pioneering work was carried out at standard telecommunication laboratories at Harlow in England, now recognized as the birthplace of optical fiber communication.
Okay, I will give that section to them. हरजोत को RIT वालों का कनेक्शन नहीं हो रहा, देखो क्या क्लास. So this was a small clip where we showed how the Charles Coe he performed this experiment with the helium neon laser, and then he could able to send the signals using helium neon laser over the optical fiber, and on the basis of which he proposed that optical fiber can be used as a communication medium. So this is the basic fiber optic link I mentioned. We have a transmitter now which is now the optical transmitter, where the electrical signal is converted to optical signal by using some light source. Generally, these are the LEDs or laser diode or injection laser diode, which will give the output modulated output. And on the fag end, we have the detector, which is the optical detector, which accept the light and convert it into electrical signal. Generally, these are the pin diodes or these are the APD, lunch photo diode. So electrical signal is demodulated to separate out the information at the detector end. RIT Jaipur. Now you are connected now. Rajasthan Institute of Engineering and Technology, RIT Jaipur.
Yes, sir. Thank you, sir.
Okay. So we have optical transmitter, we have optical receiver, and they are connected by optical fiber. So basically, optical communication, it deals with the three components: optical sources, optical detector, and optical fiber. So these three components I mentioned. The fiber optic system devices are transmitter, where we have the laser diode or LED. We have the optical fiber cable, which may be multimode fiber or single mode fiber. So here I want to mention that we have the one is the optical fiber, which is only core and cladding. But for practical applications, we have to convert this optical fiber to cable. So when it is a cable, it has number of many strong layers to provide mechanical strength to the fiber. Because fiber is made from glass, it's very thin, and the fiber has to be laid down in the field. As a result, a sufficient strength has to be provided. So optical fiber cables are used for the practical application. Then we have the receiver, where it may be a pin or avalanche photon. And the foundation of OFC system is basically based on the optical fiber. So it acts as a transmission channel for carrying light beam loaded with information. It is a modulated or loaded information where we travel over the fiber, and this fiber is laid throughout the field. The long length of fiber, they are installed, they are laid, and the information is sent over the optical fiber. So optical fiber, it acts as a transmission medium. So it transmits the data. So at the light pulses, so electronic pulses, they are converted to light pulses, and these light pulses, they travel in the optical fiber, and ultimately the optical light pulses, they are converted to electrical pulses. So this is how the data is communicated, and the light propagated by means of total internal reflection. So this is the basic requirement. And for total internal reflection, we need the core and cladding. The core and cladding, they are the requirement for the total internal reflection. As a result, they form the constituents of optical fiber. This is the structure of optical fiber. Mostly it is a dielectric material or dielectric core of doped silica. The glasses, they are mostly made from silica. So doped silica, and silica is doped with some material to get the required refractive index, to get the maximum transmission. So a core of high refractive index surrounded by cladding of lower refractive index. So we have a core and we have the cladding. The refractive index of core, say N1, and N2 is the refractive index of cladding. So depending upon the requirement, the refractive index of core may be constant or it may be gradually varying. So we have different type of fiber. One is the step index fiber. If the refractive index is constant, we have the gradient index fiber. If the refractive index is gradually varying. So both step index fiber and gradient index fiber, and generally dimensions are in the range of for single mode fiber from 5 to 10 micron, for multi-mode fiber around 50 micron, or initially it was 62.5 micron. The intention is to reduce the dimensions so that there should be least path difference between different modes. So the necessary condition is that the refractive index of core has to be more than the cladding to fulfill the condition of total internal reflection. So this is what we have the optical fiber. We will discuss more in detail about the this light propagation through the optical fiber by different optical phenomena. So this is the transmission losses. So I mentioned in 1970s the transmission losses were around 20 dB per kilometer, but this was again at 633 nanometer. If you calculate these losses at the higher wavelength, definitely it will be lower loss. So and there is a rapid development in the reduction of the losses. You see, in 70s losses were around 20 dB, whereas in 80s it comes from 2 dB per kilometer. So within a span of 12 years, the losses were reduced by 100 times. So a great improvement in the transmission loss. As a result, now these losses are very, very small loss if you compare with a metallic cable. So 20 dB per kilometer and 0.2 dB per kilometer, around 100 times more improvement. So communication system, they form the basis of the communication requirement. So now I mentioned there are two major communication issues. One is the attenuation. Attenuation will decide signal loss over the distance. How long my signal I can able to take my signal. How long the signal can reach. So attenuation, it put the distance limitation over the long haul system. So I can achieve more and more distance if attenuation is less. So attenuation means power loss. Reduction in amplitude. Amplitude reduces from some value to very, very small value. So we can measure by the signal to noise ratio at this point. So that is the amplitude of the signal and amplitude of the noise. Similarly, other phenomena is the dispersion, which is the broadening of the pulse. And we know in optical fiber, dispersion is an inherent property. We know the light disperse. A light is split up into 7 colors, which is the phenomenon of dispersion. Same is the criteria here. So light, the dispersion is more prominent in optical signal, and it put the bandwidth or data rate limitation. So lesser the dispersion, more will be the bandwidth or more will be the data rate. So we want both attenuation and dispersion to be as small as possible. So both these number of methods have been developed to overcome these problems. So if you look at the attenuation in the silica fiber, I will only consider it over the silica fiber because this is the basic fiber material, and most of the fiber they are made from silica. And if you look at the attenuation curve as a function of wavelength, you see we have the first window at 850 nanometer. Similarly, this is the curve, practical curve for silica loss in the silica. This is the second window, which is at 1310. Then third minimum loss is around 1550 nanometer. And in between, you will find this is a peak. This is not of a region of interest. And this peak is because of the moisture. Because we know silica is hygroscopic. So as a result, the water vapors, they get attached to silica very easily. So as a result, during the manufacturing, it is very, very difficult to eradicate the moisture content. So as a result, this peak is there. This is because of the hydroxyl group. So it is not that it is not possible, but if we have the fiber where this peak is not there, this dotted we call it as the all wave fiber. So it can be used over all the wavelength, but then it will be very, very expensive also. The process become very, very expensive. The cost, economic condition will not be fulfilled. So as a result, still we have the conventional silica fiber with this hydrogen peak, but it can be produced with very, very low loss. So as a result, this form the basis for optical windows. So 0.2 dB at 850 nanometer, 0.5 dB at 1310 nanometer, and 0.2 dB at 1550 nanometer. So it reduces as you go to higher and higher wavelength. And further, if you go beyond this, you see again the losses increase. So as a result, minimum attenuation is at 1550 nanometer. It is not possible to utilize the electromagnetic spectrum beyond 1550 nanometer. We know that if you go to the higher wavelength, the loss will come down. But on the other hand, the frequency will fall. The wavelength will increase, the frequency will come down. So at the cost of bandwidth, we have the attenuation. But attenuation is, of course, more important than the bandwidth. So if you look at the dispersion, we will discuss more in detail later on. But dispersion, if we have the multimode step index fiber, we can have multimode gradient index fiber. We can have single mode step index fiber. So as a result, you see that dispersion is minimum in the single mode fiber. So as a result, mostly we use the single mode fiber for high data rate. Multimode fiber can be used for low data rate, but for high data rate, the single mode fibers are more preferable. So dispersion is minimum in the single mode fiber, but still it is at 1300 nanometer. If you go to the higher wavelength, the dispersion increases. So for attenuation point of view, going to higher and higher wavelength is preferable, is better. But for dispersion point of view, going to beyond 1310, the dispersion increases. So it means lower data rate. So as a result, we have the optical windows. Both these 1310 and 15 nanometer windows, they are both active windows. Both have importance depending upon the requirement, depending upon the goal. Whether my goal is to reach at the longest possible distance or my goal is high data rate. If I want high data rate, I can use 1310 window with the conventional silica fiber. If I want longest distance, I can use 1550 nanometer window because the loss is minimum. The dispersion is more. But these conditions are only with the conventional silica fiber, where we have the core and cladding. We will discuss there can be modified optical fiber, which is not a conventional core cladding, but we call these are the dispersion shifted fiber or dispersion flattened fiber. They can be used at the minimum loss and minimum dispersion, but they are different in design. Maybe difficult for manufacturer. So these we have the optical sources, which are generally LEDs, and I mentioned these LEDs, they are mostly the direct semiconductor, direct alloys, maybe gallium arsenide or gallium aluminum arsenide. They are available for 850 nanometer, 1310 nanometer, or even for 1550 nanometer windows also. They are low cost and easy to use. They are mostly used with a multi-mode fiber because LEDs, they have large, they are broad, it is a broadened source. These are incoherent and large broadening. They are not very, very narrow source. So as a result, the special type of LEDs which are, we call as the edge emitting LEDs. Normally these LEDs, they are surface emitting LEDs. Light is emitted from the surface. But if it is made as a edge emitting LEDs, the light output spectrum can be made narrower. More narrow spectrum we can get from the edge emitting LEDs. So these LEDs can nowadays, they can also be used with the single mode fiber, but with the special design. Similarly, we have the laser diodes, which can give you the better performance. Laser diode, we know these are the coherent sources. They have very, very narrow line width. They are highly monochromatic. So as a result, but they are more difficult to produce as compared to LEDs. Mostly they are the quaternary alloys. 4 alloys have to be mixed to get a diode material. So as a result, more difficult, but they can give you high output power. LEDs, they are mostly the low output power. Similarly, very high speed of operation. They can operate at very, very high speed and very expensive also. They are more expensive as compared to LEDs, cost-wise, and they need also special power supply and circuitry. So they are more prone to changes. They are more, you can say, practical difficulty to operate the laser diode, but they are available. They can give you the high power, high performance link. So we can have a combination of maybe LEDs and multi-mode fiber, or LEDs or single mode fiber, or laser single mode fiber. Mostly it is a laser and a single mode combination which is more practical beneficial. Similarly, we have the detector, optical detector. We can have, normally they are the pin diode. This is P intrinsic and N type region. So in between we want the detector to be the bi detectors. So the requirement is only how to increase the depletion region. So mostly they are the reverse bias detectors, and they are available maybe from silicon, germanium, or it may be a alloy. So generally 850 nanometer, 1310 nanometer, or 1550 nanometer window, they are low cost components. They are not very expensive. So, but these detectors, they are wide wavelength detectors. They can operate at different wavelengths. Similarly, we can have the APDs, avalanche photodiodes. They are also mostly available with the different materials. They are available in all the three wavelengths, but only benefit is that they have high sensitivity. The pin, they have the low sensitivity. They need more power to detect the signal, whereas high sensitivity, they can operate at very low power level. They can operate at even at the nanowatt of the power, whereas for pin diode, you need minimum microwatt of the power. So APDs, they have the what we call the internal amplification. But again, they need high bias supplies, maybe 40 to 50 volt. They cannot be used with the normal 3 volt or 5 volt PCB power supplies, whereas LEDs or pin, they can operate at low voltage. So you need the high voltage, and again the construction buys, the manufacturing buy, they are expensive to produce as compared to pin die, but they are very sensitive. So we can have a different combination of our components depending upon the requirement of the system, depending upon the quality of the system. We can have LED and pin combination. We can have laser and APD combination. Best performance with the laser and APD combination, or intermediate or middle performance will be with the LED and pin combination, low cost, whereas another is the high cost. So depending upon the requirement, a service provider, a designer can choose according to his requirement, because he has to look for the capacity, he has to look for the quality, he has to look for the economy also. The service provider, the system has to be profitable. The service provider will provide the services only for the profit. If these are the commercial systems, so one have to look for the very optimum design, and these designs are goal oriented. So these are the different optical sources and combination, and we know optical fiber system, they have different advantages over the metallic cable. One is the wide bandwidth. I already discussed, they can provide extremely high information capacity. More than 3 lakh voice channel can be put over a pair of optical fiber. Then they can provide what you call the integrated services. All voice, data and video, they can put over the optical fiber. Normal copper cable, metallic cable cannot provide you these services, what you call as the ISDN services. Low loss, I already discussed, the loss is very less, 0.2 dB per kilometer. So repeated spacing can be more than 100 kilometers. Whereas in metallic cable, after every 3 kilometer or 4 kilometer, you have to use a repeater. So it reduces the repeater cost by a big amount. So it can help in this part. Similarly, interference free. So they are immune to interference. No crosstalk. The signal travel within the core. So there is no radiation, no energy loss. As a result, they are interference free, and they can be used in any harass or noisy environments. So as a result, normally if you are optical cable, a copper cable, it passes through the tube light. which is having the choke, it produces a lot of noise. So whereas in case of optical fiber, there are no such problems. So as a result, optical fiber, even they can be laid along the high tension wire, along the power cable, along the electrical power cable. The signal will not be affected in this case. Then high security, there are no radiations, difficult to tap. Normally in our copper system or our electrical system, we know there are the Kundi connections. So you can just put the wire over the cable and you can tap the signal. Whereas in optical fiber, it is very, very difficult to tap, because if you want to tap the signal, you have to connect core to core. Highly skilled skill is required for that purpose. And even if you break the fiber, you will get the alarm that somewhere the fiber has been touched. So as a result, they are very, very attractive for defense, intelligence, and high security services. So it is a high security system. Similarly, very compact and lightweight. They are very, very small in size. Fiber thin than human hair. A single fiber cable can replace 1,000 pair copper cable, which is very, very bulky in size. So as a result, great benefit of compactness. A fiber weight is very, very small, 20 gram per kilometer, which is very, very small as compared to the copper cable. And even fiber is a very, very lightweight cable. We use very, very lightweight material with the help of in the fiber cable. Then environment immunities. So as a result, greater safeties. Fiber is a dielectric material. So no current, no short circuit. So as a result, many fire incidents are because of the short circuit. So whereas in this case, so fiber, it is a dielectric material. As a result, it is very, very extremely safe for hazardous environment like your oil and petrochemical industry. So very, very environment friendly, not prone to lightning. It is a dielectric, so there is no point of lightning. By temperature range. So a fiber, it can work at by temperature, very, very low temperature, very, very high temperature. The melting point of fiber, of silica, it is around 1410 degrees centigrade. So as a result, it can operate to such temperature, and they are very, very attractive for especially in the areas where we have to measure the signal from very, very high temperature, like our nuclear reactors. The temperature there is very, very high. So as a result, optical communication is the only solution to carry the signal from the reactor to the control channel. So optical fiber is there, and then lifelong, more than 30 years. The lifetime of a copper cable, how much? It is 10 years. After every 10 years, as per our international standard, a copper cable has to be replaced. Whereas for optical fiber, the fiber which was laid in 1977, still it is working at its full potential. So we can expect a life more than 40 years for the fiber optic cables. So they have more life than the existing copper cable. As a result, they are more cost effective. Abundant raw materials. The optical fiber is made from silica, and silica is nothing but sand. Lot of sand is available at our sea beaches. So it is not a rare material, whereas in case of the copper, it is a scarce material. One has to look for the copper ores or copper mines, whereas the silica is easily available. So it is another additional benefit of the silica optical fiber. So number of benefits are there of the optical fiber over the copper cable. No doubt the initial cost of optical fiber cable is more than the copper, but if you look at the benefits, it makes the system cost effective. You have more benefit as compared to the cost. So there are, of course, some practical disadvantages. It is not only that we should talk about the advantages. Optical fiber, I mentioned, they are relatively expensive. Connectors are relatively expensive, and they are expensive because of the high degree of precision. Because our connectors, the fiber, the outer diameter of fiber is the 125 micron. The cladding is 125 micron. A connector has to be put over the cladding. So naturally, the ferrule diameter is of the order of 130 or 140 micron. And this type of precision is only possible with the high degree of precision, high quality of machining. or mostly one use the laser machining or laser drilling or laser machining for all these applications that add to the cost. So as a result, the connectors are also expensive. The connector installation is time consuming and high skilled operation is required. You need a highly skilled person to put a connector over the fiber. Because if you look at the connector, a connector is a 3-part. So one have to put the connector over the fiber. So we have to put the ferrule, then we have to put the another component one by one. So it needs a training, a skill training, and of course it needs some time also. It is not just like our 2-pin and 3-pin, our plugs which are used in the electrical connectors. Then jointing of optical fiber. A fiber jointing is, we call it as a splicing. Splicing is a permanent joint of the optical fiber, like our soldering of the metallic wire. So splicing is done only with the what we call the optical splicers or fiber splicers. And we know in order to solder, in order to weld, it is also called the fusion welding. We have to fuse the glass. We have to fuse the fiber. And for fusion, we have to go to very, very high temperature of the order of 1400 degrees centigrade. So need very, very powerful heating source. So that add to the cost. So they are also expensive and need lot of the skill operation. So even our under our skill development program under NSDC, there is a sector there is a TSSC, Telecom Sector Skill Council. They offer this skill-based program on optical fiber splicer or optical fiber technician. The role is how to splice the fiber, how to test the fiber. So these type of skill training can also be provided under this optical fiber communication. And connector and joint are relatively lossy. There are more loss as compared to normal connector, but because we will come here in the case of optical fiber, we cannot send more power to the fiber. So a small loss contribute in this. Then difficult to tap in and out. I mentioned it as a security feature. It is more safe. But on the other hand, now we have the concept of networking. We have concept of internet. It is the same data which is provided to number of users. So we need the tapping. I have to tap the signal. I have to tap in the signal. I have to tap out the signal. So as a result, we need some what you call the couplers. And couplers, they are all the optical components which add to the cost. So on the one hand, it was the benefit, but on the other hand, it adds to the difficulties also. And relatively careful handling is required. And fiber, we know all it is made from glass. So when we come across glass, we have to handle it more carefully. Delicate to handle as compared to normal metallic cable. Although the fiber is cabled in such a manner that your glass will not break, but still it is a glass. One have to be careful in handling the glass cable as compared to the copper cable. So this is the long typical hall link I mentioned. We have in the system, we need the amplifiers, we need at different places, and at some place we may also need regenerator. So amplifiers are we call normally as a repeater, whereas in a regenerator it is a combination of amplifier and some more circuit, what we call as the timing circuit. Or we have to restore the signal, we have to regenerate the signal. It is the retime the signal or it is reshape the signal. So with the broadening, your signal may be reshaped. So one have to reshape, especially in the digital communication. The signal has to be a rectangular signal. So one have to reshape the signal. So a regenerator may be required after few repeaters. So OFC system, I mentioned mostly the existing system, earlier system, they were operating at 1310 nanometer wavelength. At this, we have the low loss, not minimum loss, but minimum pulse broadening. So these systems, they can provide high data rate, but not very, very long distance. They can give a transmission rate of maybe from 2 to 10 gigabits per second. But regeneration of the signal is after 30 to 60 kilometers, because here the loss is, Rayleigh scattering is somewhat more. The loss is around 0.4 or 0.5 dB per kilometer. So more repeaters are required, and then conversion amplification of the signal. Here there is no optical amplifier or efficient optical amplifier. So as a result, the optical signal is converted from optical to electrical. It is electronically amplified, then again converted from electrical to optical. So this is a drawback with the 1310 system, which were earlier or pre-installed system, but nowadays many improvements have been come into the system. We can have optical amplifier, but not just as you can say beneficial as the erbium doped fiber amplifier. Then the presently system mostly they are operating at 1550 nanometer window, because this window have provided more bandwidth, around 120 nanometer or around large bandwidth. Whereas for 1310 nanometer, the bandwidth provided is lesser as compared to 1550 nanometer. Here the silica has lowest loss. So system can go to long distance but increased dispersion. Not very high data rate, which is possible with the 1310. But there is a solution. Instead of the conventional silica fiber, one can use what is called the dispersion shifted fiber. The dispersion shifted fiber, DSF fiber, they have minimum dispersion at 1550 nanometer. Basically, the minimum is just like a belly window. So this window can be shifted from 1310 to 1550 by certain modification in the optical fiber designs. So it is a possibility to achieve the lowest loss and negligible dispersion, but it will add to the cost. Dispersion shifted fiber, they have different type of designs as compared to conventional single mode fiber. So economy we cannot be there in these fiber, and many other issues are there with the use of dispersion shifted fibers. But the great advantage is the signal amplification. Here the loss is less, so signal amplification will be after 80 to 100 kilometer, and there is a direct amplification of the signal in the optical domain. We can have erbium doped fiber amplifier. So this amplifier is very useful in 1550 nanometer range. It is a amplifier which is developed over the fiber itself. So it is not a coupling problem. Normally our amplifier, they are bigger in size. They are block components. When you connect the block component to the fiber, there is a size compatibility, size issue. So lot of large loss can be there. But EDFA is over the fiber. So a signal will come, it interact with the erbium doped fiber material, and we will get the amplified signal. So it is a direct amplification of the signal. Dr. Tiwari, he will discuss more in detail about these EDFAs, but there is a direct amplification of the optical signal. The flat gain, it has a flat gain over the 1550 nanometer window only. So EDFA can work at 1550 channel only. It has a huge bandwidth, around 12,500 gigahertz bandwidth. A amplifier is known by its bandwidth, but the flat gain, huge flat gain. So it can amplify all the signal bits range within this range simultaneously. Very attractive for wideband communication or multi-channel communication. Then comes the another point is how to increase the capacity of the system, network capacity, and how to address number of users. Communication system is not for one user. The system will be economical if it is used by masses. This is the scenario with the mobiles. The mobiles were very expensive in early 90s, but now the mobiles are very cheap, not very high cost. It is because now technology has been opted by masses. Similarly, my system has to be used by masses. So as a result, there are different options how to address number of users. One approach which is generally used is what we call as the space division multiplexing. Because these are the multiplexing techniques. How to mix the signal, how to multiplex the signal. Then similarly, at the another end, we need the demultiplexing. So we have to multiplex the signal, we have to demultiplex the signal. This multiplexing base, what is the space division multiplexing? You can add more and more channels, more and more wires. Like you can have copper cable, you can have a pair, you can have 100 pairs, you can have 1000 pairs, you can have more pairs. You can increase the capacity. You can have put more and more user over the cable. But you need more fibers, more cable, and expensive engineering is required. Your cable will become more bulky cable, and then duct exhaust. So these cables are always put in the ducts. So as a result, more and more it will add to the cost. More fiber, more cost, more time consuming. The other option is the time division multiplexing. So you can add the number of data over the time frame. For example, 1 second. If I'm talking about kbps, so in 1 second you have kilobits of the pulse, 1000 pulse. If you are talking about gbps, in 1 second you have gigabits of the pulse. In the mbps, in 1 second you have megabits of the pulses. In terabits you have 10 to power 12 bits in 1 second. Naturally, you can accommodate large number of bits. Your bit size has to be very, very narrow. So as a result, in order to fulfill this requirement, you have same fiber but high bit rate. High bit rate means very, very narrow pulses. So as a result, you need electronics which has to be very, very fast. How to generate these pulses? So electronics become very, very expensive. So it is difficult to achieve those type of pulses. Another approach is WDM, wavelength division multiplexing. We know in optics we have the different principles. The rectilinear propagation of light travel in straight line. There is another principle, what we can call it independent propagation of the light. All the light rays, they travel independently. A ray is traveling, assuming that there is no other ray. So basically, all the wavelengths, they can travel independently, and provided they should be different. And different wavelengths, we know they will follow different path. So different wavelengths can travel in the same fiber, provided they should be different. So we can have same fiber, but number of wavelength or number of channels. So this will become a multi-channel system. So we can have the wavelength division multiplexing. So here we will use a single fiber, but number of wavelength. So it is it is the more fiber compatible, fast time to market, lower cost, and utilizing existing TDM equipment. We can use the TDM signal for the WDM application. Your signal can be a time division multiplex. So you can utilize the existing TDM technology and the WDM technology. You can integrate the two. As a result, your capacity of the system can be enhanced a multifold. So this is again requirement WDM and DWDM concept. Here you need number of wavelength, only you need number of transmitters. So number of wavelength, they can be there. These wavelength, they are multiplexed by the multiplexer. We call it as the wavelength division multiplexer or WDM. Then in between the system, you have the repeaters, you have the amplifiers, you have the fiber, and you have many other components just to refresh the signal. And at the other end, we need the wavelength division multiplexer, because I have to separate the different wavelengths. So here we have the multiplex signal, where we have to again separate the different wavelengths. These wavelengths, they may carry same information, or they may carry different information, but they have to be different wavelengths. So it is this is a unique feature of optical fiber technology. We can combine number of wavelengths by using the technique of wavelength division multiplexing. So these systems, they are of great demand because of the many features. The main characteristics are that the WDM, they have the ability to put multiple services onto a single wavelength. So you can have TDM, you have single wavelength, you can have TDM, you can have a voice signal, you can have video signal, you can have data signal. They can be time division multiplexed, and they can be put as a video signal. First, you can integrate the TDM and then put over as a WDM signal. So we can integrate the two technology, and we can get the benefit of both the technology. So we can multiply the benefits by using the WDM system. We will discuss more in detail. So future OFC system, I mentioned, they are the coincidence of, we have the WDM technology, we have the wideband EDFA. So normally system, there is a demand, future system will be the WDM system or DWDM system. It is a dense wavelength vision multiplexing. WDM is a coarse wavelength vision multiplexing, where the wavelength they differ by more than 1 nanometer or more than 100 gigahertz. Whereas for DWDM system, the channel spacing is less than 1 nanometer or lesser than 100 gigahertz. So with the DWDM system, number of wavelength can be, number of channels can be multiplexed. So we have, and we can use what we call the solitone pulses, which are non-dispersive pulses. They can provide you terabits of the data over the long distance. 150 kilometer is the repeater spacing, say 55 wavelength. Similarly, you can have 2.6 terabits of data for 132 wavelength DWDM system. So we can have the system, only we will come across this issue again, that it is sometimes it is preferable to use low data rate but multiple channels. When you have a high data rate, number of problems will be there in the system. So it is preferable to use lower data rate but more channel. Say 100 gigabit system, you can have 10 gigabits per channel and 10 channels. Similarly, you can have 2.5 gigabits and 40 channels. It is preferable to work at the lower data rate with more channels. We will discuss more in detail and during the nonlinear effects in the OFC systems. So optical fiber communication is provide a expressway. So it is just like a lane system. Now you have the lane system from one place to another place. It is a 4 laning or 6 laning or 8 laning. So traffic can be handled very easily, and different type of traffic can be accommodated. Similarly, in optical fiber communication, it is just a expressway which can ease the communication way. So light wave communication system applying DWDM or EDFA, it can provide a zero loss and near infinite bandwidth, and it provide a network capable of handling almost all our information need. So it can provide a true information society if we have a very, very strong telecommunication system which is based on the optical fiber. So as a result, now we have different type of applications, what we call as the broadband services. It is all because of the optical fiber that it provides all type of services. Mostly in our telecommunication system, they are now the optical fiber based. All the system maybe a central exchange or trunk lines or even up to local loops, we have the optical fiber. The only place where optical fiber is not there, it is up to the end. We are not getting the optical fiber at our home, but it called fiber to the home or fiber to the premises. But still it is there in the process. We can have now these systems even up to the premises, but only the cost will add. So many companies, they have started to provide what we call the lease line. So you can have the lease line where the direct optical fiber will be there up to your place. So these are the bandwidth evolutionary landmark development. You see the optical fiber, optical fiber is deployed at rate of 1,000 miles over the globe. Huge requirement is there of optical fiber, and the ultimate aim is to connect each and every place with the optical fiber. Because with the optical fiber, the distance involved is very less. If you take the case of the satellite, whether the distance is long or short, minimum you have to cover 72,000 kilometers, 36,000 kilometers uplink, 36,000 kilometers downlink. 72,000 kilometers have to be traveled. But if you, on the other hand, in some country, like if you take the case of US, the distance, aerial distance is around 16,000 kilometers. Whereas in case of satellite, the distance is 72,000 kilometers. So if you calculate the speed of the signal, it comes out to be near few milliseconds. As a result, we always notice some delay in the signal. Synchronization problem become more difficult. But nowadays we have the fiber links. Fiber links from one country to another country, another country to another country. It is an international telecommunication system now. So with the optical fiber, the distance become around 16,000 kilometers. So these are the delay in the signal is now very, very less. So as a result, we don't find many times synchronization problem. And on the other hand, you see if you have a TDM system, the TDM technology has already reached at around 40 gigabits per second. If you combine this TDM technology with the WDM technology, you can have 80 wavelength, and TDM signal, you can have terabits of data. So terabits is only possible if you combine TDM and the WDM technology. In future, we may talk about the petabits of the data. So you can add more and more channels. You can improve the multiplexing technologies. So optical fiber technology, it can provide a huge bandwidth. That's why it is called infinite bandwidth system. Further, we can have, it is not only limited to only 1310 or 1550 nanometer bands. So we discussed only about the what is called 1310 or 1550 nanometer band. We can add more to this, because always it is not the long distance. We have the short link, we have the medium link, and if the distance is short, high attenuation is not a problem. So as a result, we can have more bands. We can utilize this window maybe for medium performance link. We can utilize another window. We can further extend this window. We can design the fibers. We can design the fiber without this peak. So in the future, we may have the fiber where this type of peaks are not there. So I can utilize the full window of optical window for all the communication link. So more channels can be added. It is not like microwave and radio wave, where the bands have already exhausted. Lot of potential is there in the optical fiber communication. And I mentioned the next step earlier, we have the system where the exchange to exchange, central exchanges are connected by optical fiber. Your trunk lines are connected by optical fiber. Even your mobile towers, they are connected by the optical fiber. All mobile towers, they are connected by the optical fiber to the trunk line. So it is ultimately the optical fiber which will come. And now the next approach is to connect the fiber to the home or fiber to the premises. The fiber will come to your place. Only, the laying of the fiber, the initial cost will be more, but looking at the future requirement, because capacity is always ever increasing demand. In order to overcome the future system, the fiber has to reach at the home. We are finding a lot of problem. We are finding all these connectivity problem, because everywhere it is not the fiber. The fiber is shifted from, the signal is shifted from optical fiber to the copper cable. And copper cable cannot have that much capacity. As a result, we have some connectivity problems. So once the system is on the optical fiber, such issues will not be there. And a lot of developments are already taking place in this area. So fiber to the premises, it is not only that we have to use the one wavelength, we can use the multiple wavelength. So you can utilize both 1310 nanometer window, I can use 1550 nanometer window, I can use the wavelength division multiplexing technology. So that is the future of the optical fiber connectivity. So data can be provided to number of users, number of multiple services can be added to the optical fiber. So this is again the 50 years of fiber optics. I mentioned it started in 70s, and now you see there is exponential growth in the optical fiber. We will see the first quarter of 21st century, it will see a exponential growth in the demand for photonics and fiber optic components. We need many components, we need more and more optical fibers are all in demand, because now the next generation our system, they will be the photonic system, what we call as the silicon photonics. And optical fiber, they are made from silica. All our computers, they will be the optical computers. All our communication, they will be through the optical signals. That is, then only the capacity is possible. I will see just a small video on this part, say how the silicon photonics.
After years of innovation in silicon photonics, Intel Labs is proud to announce the 50-gig silicon photonics link, an optical communication system and major advancement towards terabit per second data transfer. This concept vehicle is the first end-to-end silicon photonics data connection with integrated lasers. The one-piece silicon transmitter uses hybrid silicon lasers and modulators to turn data into light pulses, and a multiplexer to combine the pulses into a single signal. which travels across a simple fiber optic cable to a silicon receiver, where a demultiplexer divides the signal back into separate channels, and photodetectors turn the light back into data. Intel continues to scale up bandwidth of individual laser channels to transmit more data. And by adding channels using different colors of parallel light, bandwidth could be scaled out to more than 1 terabit of data per second over a single fiber. And the fully integrated silicon-based unit allows for the benefits of the CMOS high-volume manufacturing process. This link can eliminate data bottlenecks and enable design innovation. Data centers can be reformed into efficient banks of computing and memory that are more flexible, scalable, and manageable, and can replace the messy yellow wall of cables with just a few. Consumers would be able to enhance their mobile system capabilities by plugging into HyperDocs, the 50 gig silicon photonics link, moving forward at the speed of light.
So it is the photonics or silicon photonics which will be the attraction for the next generation systems, because it is the high speed is only possible with the photonics. So we need, I mentioned, we need number of photonic component, photonic technology, and different type of components are required, and which has lot of potential for the development, for industrial manufacturing, and all our telecommunication system devices. And this is what the Cow, when he was awarded Nobel Prize, he was asked, when will fiber become obsolete? And this is what he replied, I cannot think of anything that can replace fiber optics. In the next 1,000 years, I can't think of a better system. But don't believe what I say, because I don't believe what experts said either. In 60s, I did not believe what experts says. Many people, they opposed that optical communication is not possible, but he predicted, he proposed it, and today it has become a reality. So optical fiber, it has huge potential, and it can reach, it can fulfill the need of maybe in coming 50 to 100 years, the system will have lot of capacity to fulfill the communication requirements. So I briefly explained about the development of the system, what are the fiber optic component, what is the potential of the system. There are certain advantages, of course, and there are certain disadvantages of the system. But overall, the system is a cost-effective system. It is the only technology which can fulfill the communication requirement of the future. So I will stop here. We are already late for this in this session. The question and answer session we will take in the afternoon. So I will engage another session on optical fiber waveguiding. If you have any question, you please be ready with your questions. So we will start with the question answer session, and then we will continue with the optical fiber waveguide. So I will stop here, and thank you all the participants at all the center, and we will again connect maybe at 2:15. So we will start the session at 2:15. Okay. Okay, because sometimes it will take for connectivity. So between 2:15 to 2:30 we will connect, and we will start the session. Okay. It is correct. केबल ना आपकी ढीली हो गई है शायद, नहीं करिए ये मिश्रा जी, आपकी केबल जो है ये देखो ना, इसको जितनी पीछे से ना आपकी इधर इधर हम लोगों के हाथ लगते हैं ना कि बहुत से भी हिलेगी, सीधी आ सकती है इधर से सीधी। क्योंकि इधर से बार बार हिलेगी ना तो ठीक है। कुछ हो रहे हैं लोग कुछ कनेक्ट, तो फिर नहीं तो लेट हो जाता है ना सुबह भी करते करते हम। आज ही बोल दे रहा हो यार, ये भी ना आपका centers
Hello, hello. Hello. Hello.
The question was from night ke bana night ke day वो काम कर सुना है night function
सुबिला
सर को भी पच्चर में क्वेश्चन
मैं फर्स्ट डिस्कशन का पच्चर ना फर्स्ट जो पच्चर को कॉलेज रे
ସେମାନେ चेक करते जाता है
चेक करे अच्छा काइन जो कौन बोल जो कोऑर्डिनेटर ना कोई पच्चर
ये रूम में कितने लाइट के मुझे
So I'm lighting to Boston. Strong test for
अभी पच्चू में ऐसे ही सर
और ना connect well. So connect those and solve the same question and answer.
Hello, good afternoon. All the participants at different order centers. Am I audible at your place?
Yes, sir.
So in the morning session, I gave an overview of OFC technology, and we discussed different parts, the potential of optical fibers, then different type of other component, our optical sources, optical detectors, and later developments or future of the OFC systems. So in case any participants, they have query about the what we have discussed in the first session, he or she has any question, he is most welcome. So you can ask your question from any of the nodal center.
Hello.
If any of the nodal center he has any question, he or she has any query, he is most welcome.
Hello. Hello, sir.
Hello.
Hello, sir. Good afternoon, sir.
Some Barampur Gate.
Okay, good afternoon.
Okay, sir. I am come from Barampur Gate College, Odisha.
Yeah.
Sir, I have a questions regarding the basic questions in optical communications. So what is the exact meaning of scattering and dispersions?
Okay. Scattering, basically I will discuss tomorrow on transmission characteristics. Scattering means when the light comes, it changes its path.
Okay, sir.
So it goes in different direction. That is what we call the scattering.
Yes, sir.
And dispersion is basically what we have light. Like if you have ordinary light, it comprises of 7 wavelengths.
Sir.
So light split up into 7 colors. That is called dispersion.
Okay.
So scattering is a loss that contribute to attenuation, and dispersion that contribute to broadening of the pulse.
Okay, sir.
Both are different issues.
Sir. Sir, another question, sir. You are saying that interference is 0 in optical communications.
Repeat, please. Pardon?
Sir, actually, you are saying that the advantages of this optical communication is interference of the signal is 0, or there is no interference of the signal. Hello?
Yeah. Yeah.
Sir, my question is, if interference is 0, regarding the nonlinear effect, actually I am working in FWM, four-way mixing nonlinear effect. So,
I'm not saying the interference 0, interference is minimum, very small.
Okay. So there is some interference with the signals.
Yeah, definitely. That's why signal get deteriorated.
Okay, sir. Sir, another question is regarding the windows. There are 3 windows that is called 850. First window, second window is 1310, and third window is 1550 nanometer.
Yes.
Sir, actually, can you please again tell me why within this 1310 and 1550 nanometer the peak is again more, the signal peak?
The signal is because of the moisture content. You know, silica is a hygroscopic material.
Okay, sir.
And when the fibers are fabricated or manufactured, the temperature is more than 1500 degrees centigrade. So at that temperature, some water vapor, they get trapped into the fiber.
Achha.
So it is because of the OH ion absorption which contribute to the peak between 1310 and 1550.
Okay, sir. Okay, thank you, sir.
Thank you.
So if we can completely eradicate OH content, then this peak will not be there.
Okay, sir.
But that makes a process very expensive.
So that is due to the moistures only.
Yeah, that is due to moisture.
Moisture vapor content.
Yeah, water vapor content.
Okay. Thank you, sir. Thank you very much.
Okay, thank you. Question from any other nodal center?
Zero loss
Question from any other nodal centers? In case any nodal center have any question or any query, he or she may ask. Otherwise, we will continue with the next session. So no question from any nodal center?
Hello?
Hello?
Hello, can you hear me, sir?
Yeah, I can hear you.
Hello? Sir, RIT Jaipur.
Yeah. Do you have any query?
Sir, my question is that you told us that the optical sources are made in the range of 850, 310 and 1550.
Yeah.
So if attenuation is more in 850 nanometers, then why we are using 850 range?
No, 850 nanometer sources are very, very cheap. Gallium arsenide, the cost is very, very less.
That is the only reason we are using.
Yeah, we can use these sources for very, very low cost systems. And secondly, now these sources, they can be utilized for these local area network because distance is not large.
Okay, sir. And why we are not using the range 850 to 1350, 1300?
850 and 1300? Please repeat.
Yeah, in between that we are not using that range. Why we are not using that range for the construction of optical sources?
No, we use all the sources. 850 nanometer sources we will use, and they may be the future sources for fiber to the home because distance is not large.
Okay.
And
okay,
even
sir, thank you.
10 systems are there, 15. All these three windows are active windows.
Okay, sir. Thank you, sir.
Yeah. So any other questions? So if there is no other question, let me start with the next session. So in the morning, I discussed about the OFC system, and I mentioned that we have basically in OFC, we have three components. One is the optical source, we have the optical fiber, we have the optical detector. But the major contribution is because of the optical fiber. Because we want the signal has to be propagated over long distance, and the properties of optical fibers are very, very important. And the fiber is in the field, and these are mostly affected by the field effects. So I will discuss now in this session. First, we will discuss the optical fibers. Then tomorrow we will also discuss optical sources and optical detectors. So optical fiber wave guiding is the major requirement for transmission of optical signal. And I mentioned for optical wave guiding, we have a optical fiber which comprises of core and cladding. So it is a long cylindrical dielectric waveguide, usually of circular cross-section. It is a cylindrical fiber, transparent to light over the operating wavelength. The fiber has to be manufactured in such a way that whatever operating wavelength you choose, it has to be optimized for that wavelength. It means at that wavelength, there should be maximum transparency. If you are using 850 nanometer window, your fiber has to be optimized for 850 nanometer. If it is 1310, it has to be optimized for 1310, or maybe for 1550, it can be optimized. But looking at the scenario, many times even 1310 or 1550, there is not a major difference in attenuation. So the fiber may work at both the windows, but definitely the performance for the two channel, both the channel will not be similar. So optical fiber, we have core, we have cladding, and sometimes it is covered with a buffer coating. So when I talk about optical fiber, it is core and cladding, and buffer coating is just required to protect the fiber. If the fiber is to be transported, then buffer coating is required. But actually, for practical application, there is no buffer coating. If it is a cable, then buffer coating is not there. Sorry. So inner part is a core of any radius A and refractive index N1, and outer layer is a cladding layer which has refractive index N2, and N2 is always less than N1 in order to fulfill the necessary condition. Because total internal reflection is only possible if light goes from denser to rarer medium. And this total internal reflection took place at the core cladding interface. So at this interface, the light will go from core to cladding. So from denser medium to rarer medium. So refractive index of core has to be more than cladding. So this is the first requirement for the manufacturing of optical fiber. So total internal reflection, I mentioned, you need cladding to protect the fiber or to make the light propagation more effective. So better wave guiding. If cladding is not there, suppose there is no cladding, then there will be air. So total internal reflection condition will still be fulfilled because you are going from glass core to air. The refractive index is less, but here the base, any light which is incident at core clad at the surface, there will be more loss. If it is a cladding of very near refractive index, then this radiation loss will be very, very less. There will be no leakage if there is a cladding. So as a result, we get all around, if there is cladding, we get around 100% total internal reflection at core cladding interface. So this is the one requirement for the cladding over the core. Then in order to further understand this wave guiding transmission of light, we know that fiber is a very, very small or dimensions approximating to human hair or of the order of micron size. So we have to necessary to consider the optical wave guiding for a glass fiber. So when we consider the wave guiding, we know in optics, the fiber, it is we call it as the open optical wave guide. If you remember, in the microwave cavities, they are all closed cavities. But here, the optical fiber, both the ends are open. So we call it the open wave guide. But there are the boundaries. Boundaries are locked. So boundaries are made by core and cladding interface. So it is bounded along the core cladding surface, but ends are open. So we call it as an open optical wave guide. Now when we analyze the fiber, it depends the optics. So in the optics, it depends what are the dimensions of our wave and what are the dimensions of aperture. So in optics, we have two types of theory. One is the geometrical optics, other is the electromagnetic wave theory. So geometrical optics, or we call it as the wave theory. This is, we know the geometrical optics is applicable if we say A over lambda is large. So A is the diameter of the aperture and lambda is the wavelength. So if A over lambda is large, geometrical optics is applicable. So we call it as small wavelength limit. So small wavelength limit, so we can apply the geometrical optics, and if dimensions are smaller, if A over lambda is less, then we have to apply the electromagnetic mode theory. So both the theories are there in the optics, so geometrical optics and mode theory. So if we look at this geometrical optics, we have the two type of optical fibers. If you have a multimode fiber, I mentioned that multimode fiber, they are generally of dimension 50 micron. And this wavelength is of the order of 1 micron. So A over lambda is maybe around 40 or around 50. So this is a large number. So we can apply the geometric optics. So in multimode fiber, the geometrical optics is fully applicable. But if you have a single mode fiber, the dimensions are 8 micron. So 8 micron, the wavelength, if you choose say around 1.3 or 1.5, this number will be around 4 or 5. So in this case, this is not, A over lambda is not large. It is comparable to 1. So aperture and wavelength, they are comparable. So in that case, geometrical optics is not applicable. We have to apply the electromagnetic mode theory. So in both the cases, when we have a multimode fiber, we can fully rely on the geometrical optics. But when we have single mode fiber, we have to go to the electromagnetic mode theory. So geometrical optics will not be fully applicable. So we will consider in the wave guiding, we will consider both the theories. because it is easier to understand geometrically. We are more familiar with the rays and other geometrical parts, but electromagnetic mode theory, here one have to go for all the Maxwell equations, lot of theoretical calculations and numerical methods have to be applied for all these calculations. But it gives us the complete picture of the waveguide. So we will use both geometric optics to understand some basic parameters, and then we will go for the mode theory where geometric optics is not sufficient to explain different phenomena. So I hope everybody is familiar with the total internal reflection. We know the light, when it enters from denser to rarer medium, so at the interface it undergo reflection, it undergo refraction. And we know that angle of incidence and angle of refraction. When it goes from denser to rarer medium, the angle of refraction is more than the angle of incidence. So we get the refracted light. And further, if we go on increasing the angle of incidence, the refracted angle goes increasing, or we say the refracted ray bend away from the normal. If you further go on increasing the angle of incidence, we will find at one place the refracted ray, it travels parallel to the axis, or we find the reflected angle is 90 degrees. So in case of refraction, we apply the Snell's law. So N1 sin phi 1 equal to N2 sin phi 2. And when light go from denser to rarer medium, the angle of refraction is always greater than angle of incidence. And in limited case, when the angle of refraction is 90 degree, so in that case, your sin phi 2 will be 1. So we can write it as N1 sin phi 1 equal to N2, or we call it as the critical angle. So critical angle is the angle at which the refracted ray moves parallel to the interface. So this is, we call it as the critical angle. And if you further increase this angle, the light will go to the same medium. So this is what we call the total internal reflection. So in order to get total internal reflection, the angle of incidence should be greater than the critical angle. So this condition have to be maintained or have to be fulfilled in the optical fiber. So light should incident at the core cladding interface at angle greater than the critical angle. So this is very, very important for the light to propagate. Otherwise, light will not propagate. If the angle of incidence at core cladding interface is less than the critical angle, the light will not travel in the optical fiber. So this angle is important to measure. And we will find, if you look at this equation, we can write sin phi c equal to N2 over N1. So this critical angle phi c, it depends upon refractive index of core and cladding. So what is the refractive index of one medium to the other medium? So total internal reflection will take place. So at angle of incidence greater than the critical angle, the light will reflected back into the originating medium, and we get total internal reflection with high efficiency. We want this light to be travel very, very efficiently. So in total internal reflection, almost 99% of the light should reflect back into the same medium. So this is only possible if our refractive index or core and cladding, they are optimized. So this is how the light travel by total internal reflection. We get the light, it enters the fiber, and at the core cladding interface, it undergo total internal reflection. At different locations, it travel like this. So you will, in the optical fiber, there will be millions and trillions of internal reflection. So it means I should know what is the critical angle. So in order to find the critical angle, this angle is within the fiber, it is not possible to measure it. So, but I know the geometrically that this angle can be related to this angle is 90 degree. So this angle will be 90 degree minus phi. So geometrically we know if you have two parallel lines and we have a transversal, we have the different angle, the alternate angles are equal, corresponding angles are equal, vertically opposite angles are equal. So we can apply that geometry. So I can, in order to find this angle, I can calculate this angle outside the fiber. So if you look at this angle, this geometry, you see This is the angle of incidence. So light is entering at the fiber at the entrance and it is in the air. So this light is coming from a source and this light should be incident at a specific angle. So if we find this is the core cladding interface, this is the critical angle, this is pi by 2 minus phi c, and this angle will also be pi by 2 minus phi c. So this angle is called the acceptance angle. So acceptance angle is basically the angle at the air and core interface, so that the core cladding angle should be greater than the critical angle. Then only the light will be travel. So if this angle is beyond certain value, so light will not be traveled by total internal reflection. So it will be go out of the core cladding interface and it will be lost. So acceptance angle is very, very important. So acceptance angle, it will decide the value of the angle of incidence at core cladding interface. And this angle of incidence has to be greater than the critical angle. So we call it as the acceptance angle. So acceptance angle is the angle at which the light should enter the optical fiber, so that it should travel by total internal reflection. So ultimately we know the fiber, it is a cylindrical fiber, so it will form a cone. So we may call it as the acceptance cone and or half conical angle. This is the half conical angle, and we know this angle may vary from 0 to any value. So this value will be decided by N2 over N1, refractive index of cladding and the core. So acceptance angle, if you look at this angle is the maximum angle. Any angle beyond this angle, so light will not travel by total internal reflection. So acceptance angle is the maximum angle to the axis at which the light may enter the fiber in order to be propagated by total internal reflection. So this angle at core cladding interface, this angle is decided by acceptance angle. So acceptance angle is very, very important. So source to fiber coupling is very, very important. The light should enter the fiber at certain specific angle, defined angle, which we call as the acceptance angle. So acceptance angle is one parameter for source to fiber coupling or fiber to fiber coupling. So then we define another parameter. Now acceptance angle is always measured in terms of angle, maybe 20 degree, 30 degree, 40 degree, and any value. But we normally today we talk about the digitization, or where we talk about the numbers. So if you talk to anybody in terms of the angles, it is not, he may not be comfortable. But if you talk in terms of the numbers, he or she will be comfortable. Everybody will understand the numbers. So numerical aperture is basically converting these angles to the number. So it is also called the light collecting ability of the fiber. How much amount of light is collected, and also the figure of merit of the fiber. So larger the numerical aperture, greater is the amount of light accepted by the fiber, and it is related to the acceptance angle. Numerical aperture is sin theta. Okay, let me just arrange it. यहाँ पर आके जो कुछ चेंज हो जाता है. हाँ, सिस्टम टू सिस्टम वेरी कर रहा है. मेरे लैपटॉप पे ऐसा नहीं आता. Anyhow, so numerical aperture is basically sine of the acceptance angle. So you can convert this angle into numbers, because trigonometric ratios are always in number 0 to 1. So we can talk in terms of number because it is easier. So numerical aperture is n1 square minus n2 square. So refractive index of core square minus refractive index of cladding square root. So if I know the core and cladding refractive index, I can find what is the numerical aperture of the fiber or what is the light collecting ability of the fiber. So if you see, the numerical aperture varies from maybe 0.1 to 0.2 for single mode fiber. So single mode fiber, it means 0.2%, 0.2. So it means 20% efficiency. So single mode fiber, they accept very small amount of the light. They are very, very narrow. So similarly, for multimode fiber, the numerical aperture may vary from 0.2 to 0.5. They are bigger in diameter and they may differ in the refractive index. Whereas for single mode fiber, the refractive index of core and cladding is very, very near to each other. They only differ at the third decimal place. So small numerical aperture means very, very narrow angle. 0.1 means this sine theta, the theta has to be very, very small. For numerical aperture to be 1, theta is to be 90 degree. For numerical aperture to be very, very small, so for say 0.5, it has to be 45 degree, 1/2. So it all depends upon the theta. So numerical aperture is very, very small for the single mode fiber. So they need very, very narrow sources. So numerical aperture is the one parameter from the for the fiber point of view. It is one of the parameter which has to be specified. So again, now if you in the numerical aperture, if I want to calculate the numerical aperture, I should know what is the refractive index of core, what is the refractive index of cladding, and these parameters they may vary. So they are the absolute values, but mostly in the science we talk about the relative values. It is easier to maintain the relative difference. So numerical aperture, we define another parameter that is called the relative refractive index difference. This is the difference of refractive index of core and cladding. Because when in the manufacturing process you have a core, you have cladding, and during the manufacturing both are the concentric layers and they are manufactured simultaneously. So if there any parameter change, the difference will not change. The difference of refractive index will not change. The absolute value may change, but difference will not change. So we always consider the refractive index difference, that is called the delta. Delta is the difference of difference of refractive index of core taken as n1 square minus n2 square over n1 square plus n2 square. So in optical fiber, the refractive index difference is very, very small. So as a result, I can write it as n1 square minus n2 square over 2 n1 square. And I can further approximate it as n1 minus n2 over n. So approximately it is difference of refractive index of core and cladding. So we mostly use the refractive index difference. It is very, very useful for the manufacturers for the measuring of the parameter. So measuring the difference is easier as compared to the absolute value. So we always go for the relative. These are the relative values. Or I can write 1 minus n2 over n. So numerical aperture can also be written as n1 into 2 delta square root. So I can substitute, I can just translate it in this form. I can write the numerical aperture is n1 square minus n2 square root. So it is 2 n1 square delta square root. So I can write n1 2 delta square. Now in order to calculate numerical aperture, what is required? I need what is the refractive index of core and what is the difference of refractive index. So I need only one absolute value. Other is the relative value. So numerical aperture is independent of core and cladding diameter. It only depends upon the refractive index. Refractive index of core and cladding, and it holds for fiber of diameter as small as 8 micron. Because we derive it from the geometrical optics. So we use the ray concept. So it is up to 8 micron. So for multimode fiber, it is equally very well applicable. But if you go for the fiber with diameter less than 8 micron, that this definition may not be very, very precise. So then we have to consider the mode theory. So this is one of the parameter, numerical aperture, acceptance angle, or relative refractive index difference. These are the parameters which are required for the which are basically the specifications for the optical fiber. But the refractive index of core, and for the designer point of view, numerical aperture is very, very important. And this numerical aperture, it helps me to choose that type of the source, because I want the numerical aperture of the source should match with the numerical aperture of optical fiber for efficient coupling. So then we have the electromagnetic mode theory, and we know this electromagnetic mode theory For detailed understanding of propagation of light in the optical fiber, we have to consider the electromagnetic mode theory, where light is considered as electric and magnetic field. We all know about the electromagnetic mode theory, and here, in order to apply it, we have to solve the Maxwell equations. Maxwell equations for electric field, Maxwell equation for magnetic field, and we know the solution of these Maxwell equations. It form a very complex analysis, but we will go here only for the qualitative aspects to understand these parameters, because we have to we should know about the parameter of the fiber. So Maxwell equation, we know, everybody know, working in the communication, we have 4 Maxwell equations depending upon the type of the field. So these Maxwell equations can be further simplified by separating the field. We can have further convert these equations into the second order differential equations. So we can use different method of separation for electric field. Similarly, for magnetic field, we have wave equation for the electric field. We have the wave equation for the magnetic field. Delta square H equal to epsilon mu del square H over del T square. Similarly, del square E over del T square. So these are the permittivity and permeability of the medium, or maybe of the air or of the medium. For air, these values are taken as 1, whereas for medium, they have certain specific value. We may call these the relative value. So we have wave equation for electric field and the magnetic field. In general form, the wave equation is written like this: del square psi equal to 1 over Bp square over del square psi over psi t square. This is the phase velocity, and your del square, it may be have different component. It may be in the Cartesian coordinates, it is x, y, z. In the cylindrical coordinate, it is r theta phi or r phi and z. So, and this is v is the phase velocity. Phase velocity is basically, we know the wavefronts. Wavefronts, all the locus with constant phase. So they should be in the phase. All the points on that plane should be in the phase. So this is a phase velocity with which the light or with which the wavefront travel. So for planar waveguide, we can have x, y, z coordinate or Cartesian coordinate. So this equation can be taken as del square psi x square y square z square. Similarly, for cylindrical coordinate, we have to use r theta phi. So we have to use the cylindrical coordinates. So depending upon the requirement, if you have a plane waveguide, we can have the Cartesian coordinate. If we have the cylindrical waveguide, we have the cylindrical coordinate. So one have to solve the equation in that environment. So and we all know that for the differential equation, second order differential equation, the solution of wave equation is always a sinusoidal wave. We have sine plus iota cos theta type of solutions, or I can simply write in the exponential form. So psi equal to psi 0 exponential omega j omega t minus kr. This have the position variable. This have the time variable. This omega is the angular frequency, and k is the propagation vector. So all these are the standard solution in the mathematics, where we solve the second order differential equations. And in general form, I can write any field. This is equal to ei a0 exponential j omega t minus kx. So this is the polarization vector, and a0 is the amplitude of the field, and again omega t and kx, these are the exponential part. So one can have a position vector, propagation vector k. For the free space, it can be written as 2 pi over lambda. So lambda is the wavelength of the light. So I can write propagation constant in terms of the incident light, wavelength of incident light. A is the maximum amplitude, and omega, angular frequency. We know angular frequency, omega is 2 pi nu. Nu is the frequency of the light. Or I can write it as 2 pi c over lambda. So this can be related to the property of the source. And if one is interested to polarization, then E vector can be considered. It can be parallel, it can be perpendicular, or it can be any angular. So all these are the known factors in any of the wave equation. So then we come to the mode. in electromagnetic theory, it is the mode. Like in geometric optics, we talk about the ray. So ray carry the optical energy. Whereas in electromagnetic theory, mode carry the optical energy. Mode is some sort of distribution. It is not like a ray. So it is a mode. It comprises of your electric and magnetic field. It is some sort of oscillating field which carries electrical and magnetic components. So we know the wave comprises of core of refractive N1 and cladding of refractive index N2. And the wavelength, when light enters the fiber, it is affected by the refractive index. So wavelength now will be lambda over N1. Similarly, propagation constant in the medium is beta. Beta is N1 into K. So they are multiplied by refractive index of the medium. We know your refractive index is C over B, or I can write B equal to C over N1. Similarly, I can write wavelength over N1. So this is the propagation constant. Now, in order to understand, I will simply first take the case of a planar waveguide. It is a two-dimensional waveguide with Z component and X component. So I have a Z propagation, I have a X propagation. But I define the acceptance angle. So light is incident at certain angle. So light is incident at this angle, say angle theta, and this is the acceptance angle, and this angle will decide about the angle of incidence. So angle theta is chosen in such a way that light enter the core cladding interface at angle greater than the critical angle. So whenever we have any vector, in mathematics, if we have to solve any vector, we always resolve it into components, a rectangular component. So we have the say k sine theta, we have k cos theta. So these components, and we solve these components because we are very comfortable with the cos theta and sine theta. Cos theta, cos 0 and cos 1. So value will vary between 0 to 1. So by solving these equations independently by horizontal component and the perpendicular component, then in order to get the magnitude of the vector, we again go for the resultant of 2. So resultant of 2 components, then we get the magnitude. So this is how we solve. Similarly, here we can also resolve this component into Z component, which is N1 K cos theta. We have the sine component, which is N1 K sine theta. So this is perpendicular component, this is the horizontal component. So when these components will travel, what will happen? The Z component, it will travel. Whereas the X component, it will go toward the core cladding interface, and then it will form a standing, it will be reflected back because there is a reflection. It is a total reflection. So this component will go and it will be reflected back. Similarly, this component will travel. So we have now, when the light, you have a waveguide, light is entering from plus angle and minus angle, both the direction. So two waves, they will enter at the same angle. So when they enter at the same angle, they will travel and they will interfere also. So when they will interfere at different points, so we know the interference. Interference is decided by the angle, by the phase. What is the phase between two components? We have the constructive interference, we have the destructive interference. So as a result, at some point where we have the constructive interference, we have maximum intensity. Where there is a destructive interference, we have minimum intensity. So we have maximum intensity, we have minimum intensity. And phase can be opposite. So we know the phase, it can be 0 degree phase, it can be 180 degree phase. So we have positive value, we have the negative phase. So this will occur at 0 value, this will occur at 180 degree. So positive and negative. At 0 cos theta is 1, at 180 degree cos theta is minus 1. So you have both positive and negative values. So as a result, when these type of wave travels, you have at some point you have maximum value, at some point you have minimum value, and it will form what we call as the sinusoidal wave. So it is a sinusoidal solution of the wave equation in a medium. So you will see when this type of, so what will happen, I mentioned when the total phase change of two reflections is equal to 2 pi we have the constructive interference. If it is different, we have the destructive interference. So always the intensity will vary from 0 to maximum value, and we call it as in x direction it will form a standing wave. A standing wave, the amplitude remains same, but in the z direction it is changing. So when you add both the components, horizontal component and perpendicular component, we will get a sinusoidal wave. So ultimately we call it as a sinusoidal bearing wave in the z direction, because we have to consider along the distance. So along the z direction, ultimately we have a sinusoidal wave, and this wave, it has constant amplitude in the x direction but varying amplitude in the z direction. So any wave which has stable distribution in the x direction and a periodic z dependence is called a mode. Periodic z dependence means sinusoidal variation. So out of number of solutions, we know when you have a wave equation, we have number of solutions. Similarly, in the quadratic equation, we have the real root, we have the imaginary root, and basically these are the real root which contribute to the power square, amplitude square. So a stable field distribution basically is the solution of the wave equation where we have the real roots. So any stable field distribution in the x direction with periodic z dependence, we consider it as a mode. So there are a number of modes, and because we consider it as a cos theta, sin theta. Theta angle can vary. Angle theta can vary within the acceptance angle. So if I say acceptance angle is say 42, the angle theta may vary from 0 to 42. It can have any value. So we call these are the discrete values of angle of incidence. So accordingly, the rays may enter a different angle. Similarly, modes may enter a different angle. So we call these are the discrete angles or discrete modes. So there may be different modes corresponding to different value of theta, because all the modes they enter at different angle. So number of modes will be there, and we know that all these modes they have the periodic z dependence, which is given by exponential beta z dependence. Similarly, they have the time dependence, which is the time dependence. So space z dependence, time dependence, because they are oscillating. They have the frequency of oscillations. So both z dependence and time dependence. And if we combine both time and z dependence, we have this type of solution. So we have exponential j omega t minus beta. So any mode, the solution of wave equation can be written in terms of these modes. So it depends what is angle of theta. If theta is very near to axis or angle is near to 0, we will call it as the zero order mode. If theta is more, we will call it as the higher order mode. So it can be zero order mode, first order mode, second order mode, third order mode, and so many. So there can be number of modes. This is how incremental you can consider. So within a 142 angle of 42 degree, you can have 42 angle of 42. You can have angle variation of 0.1, 0.01, 0.001. Very small incremental you can consider, because in the numerical method, it is the increment which is important. If you take the large numbers, the solution will be more precise. So we have the zero order mode. So if you look at the zero order mode, like here, you see, it is like this. The distribution of the mode is like this. The intensity is maximum at the center, and nowhere it will fall to 0. So within the core, there is a intensity. But if you go for higher order mode, you will see here the light go from maximum value to 0 value. So I may call it, this is called the first order mode. It has 1 0. In the zero order mode, there was no 0. So where the field cross this boundary, we will give it the number, say, order of the mode. So in this case, this is the first order. Here it crosses twice, second order mode. Here it crosses 3 times, third order mode. And you see, in the first order mode, the intensity was maximum at the center. Whereas in the first order mode, the intensity is not maximum. There are 2 points. The power is distributed. Similarly, if you go the higher and higher order, there is more distribution of power. The power points are at 3 points. Similarly, power is distributed among 4 points. So more the points, more the distribution, more will be the variations. So we define it as the mode. So we have lower order mode, we have the higher order mode. They are associated with the mode number. So I can call it as M. M, it can be 0, it can be 1, it can be higher and higher order mode. So mode number is the parameter. So I can designate a mode with the M number. What is the value for M? If M is 0, 0 order mode. If N is 1, first order mode. If N is 2, second order mode. But mostly 0 order mode, we call it as the fundamental mode. Because here the light intensity is highly concentrated at the center, or it is a symmetrical mode. It has Gaussian distribution. Other modes are not having proper distribution. So they are easier to understand and easier to calculate for the values. So this is how the light comprises. So when the light, so what will happen? So light, it will enter the fiber at different angles. So different angle means different modes or different path. So as a result, the mode which will enter at the fiber at very, very small angle, it will choose different path. The light which will enter at large angle, it will choose different path. And the fiber, the refractive diagonal core is same. So that lead to what is called the path difference. If they have different path difference, they will travel with same speed, so they will reach at different time. So there will be delay between the mode. So this will what happen. So you have different type of modes. They enter the fiber. So some mode they will travel faster, some mode they will travel slower. As a result, they get separate. So this is what called different modes are excited. So your information, whatever your information was loaded from over all these modes. But when these modes they enter the fiber, they get separate. So as a result, your information also get distributed among different modes. And at the end, I have to collect the information. So it means I have to wait for all the mode to reach. This is what lead to what we call as the delay or dispersion. All the mode they will not reach at the same time because they are incident at different angle. They are associated with different mode. So first order, second order, third order. So these mode they will travel faster. These mode they will travel slow. So this is how the information is sent or travel in the optical fiber. So you started with the same type of distribution, but when it will enter the fiber, it is the inherent phenomena of the optical fiber, and when it enter, they get separate. So they travel, follow different path, and at our detector, they reach at different time. It depends upon what is the response time of the detector. So all these modes, they should reach within the response time of the detector. If any mode will not reach within that time, so that information is lost. So this is how different modes travel. So similarly, now depending upon the mode condition, orientation of the mode can be horizontal, mode can be perpendicular. So we call it as a transverse modes. So any mode which is in the 90 degree or perpendicular to the direction of propagation, we call it as a transverse mode. So depending upon condition, there may be many situations. If we have a electric component in the direction of perpendicular to the direction of propagation, we call it as the transverse electric mode. Because we have the Z propagation, we have the X propagation. So if Z component is 0, there will be X component. So transverse electric mode, if you see the electric field is perpendicular to the direction of propagation. So Ez equal to 0, but Ex is there. We have Ex and Hz. Hz will be there because electric and magnetic field, they are always perpendicular to each other. So if you have only H component along the direction of propagation, then electrical component will be perpendicular to the we are talking about the Z axis and X axis. So transverse axis. Similarly, if the magnetic field is in the transverse direction, so we call it as a transverse magnetic field. So we call these as the TE and TM modes. This is the simplest solution. But practically it is not like this. So this will only happen if you align the field. But practically we have many hybrid field also. So I can designate TEM. So if M is 0, I will call it a TE0 or TM0. So 0 order mode, TE1, TE2, TE3, different type of mode there. 0 order, first order, second order. But they have different distribution. So there can be hybrid mode also. We call these are the electromagnetic mode. These are the pure, it is a pure electric mode, it is pure magnetic mode, but there will be a contribution of 2. These are the TEM modes. So they can be also designated like MN with the M number, mode number. Okay, so T mode and M modes. So I hope you now could follow somebody the mode. So you are clear about ray and the mode. So in electromagnetic theory, we consider the direction of propagation as a mode. The optical energy is carried by the mode. Whereas in geometrical optics, the energy is carried by a ray or wavefront. So now we can have number of modes, different type of modes are there in the fiber, depending upon the angle, depending upon the geometry of the or configuration of the optical fiber. So then we have another parameter. I talk about the phase velocity. Phase. All the waves, all the points are in phase with each other. So, and we can define this wave velocity as omega over theta, omega over beta. And we know omega is 2 pi nu or 2 pi c over lambda. Beta is 2 pi over n1 into 2 pi over lambda. So they are a function of wavelength. They depend upon the wavelength. So is my wavelength a unique wavelength? Because I am getting this light from the source. And no source is monochromatic. Even laser is not a monochromatic source. It has high degree of monochromaticity. So my wavelength is different. So if the wavelength differ, my phase velocity will change. So practically your phase velocity will change form what we call as the group. So we know that in our even sound we talk about the beat formations or group formation or wave packets. So if you have a similar type of frequency, because these frequencies are very, very similar. You may have 1550 or 1549 or 1551 or 1549.9. They are very, very near frequency. If you have a very, very near frequency, they will form a group. So when very near frequency they travel, they will form at somewhere they are in phase, at somewhere they are out of phase. So they will form a bigger group. We call it as a wave packet or group. And this will consider the variation in wavelength. So we define a group velocity as delta omega over delta beta. We consider here change in frequency or change in propagation constant. So this will be your delta omega over delta lambda, delta beta over delta lambda. So we define it as group. So practically in the optical fiber, it is the group velocity which is important, not the phase velocity. So practically the light travel in the optical fiber with a group velocity. So it means we have to consider the variation of with respect to the wavelength. So group velocity, we simply know the phase velocity is c over n1, and the group velocity is written as c over n1 minus lambda dn over d lambda. If I calculate d omega over d lambda and d lambda over d beta, or d omega over d lambda and d beta over d lambda, and if I substitute those values in the group velocity delta omega over delta beta, I will end up this solution. So this will account variation of refractive index with the wavelength. Now what will happen? I consider the refractive index as n1, but we know the refractive index, it has small dependence over wavelength. So if you consider the variation of refractive index with the wavelength, it means I'm considering the variation of speed, or I will consider the variation of delta omega and delta beta with respect to wavelength. So we call it as the group index. So basically the index is not for the wave, but it is for the group. So we call it as a group index. So group index will take into consideration variation of refractive index with respect to lambda. If there is no variation, this will be 0. So we have N1. If it is a variation, this has to be taken into consideration. So group velocity, see, will have to be considered. So group index and group velocity, these are the two parameters of interest. Similarly, another value I want to introduce here, we talk about the field. Generally, when we have a wave, I mentioned A0 exponential j omega t minus kx. This is the field. But when what will happen? It will be true if the light travel in the core. But in some cases, light goes to cladding also. So when it enters the cladding, the refractive index of cladding is different than core. So behavior will be different. The amplitude of the field will be different. So whatever field goes to the cladding, we call it as the evanescent field. So here you see that wave, the field, the transmitted wave field in the cladding, it is not in the same form as that of the core. It will be like this: beta 0 exponential this factor at the same exponential j omega t minus beta. So if you look, this field is called evanescent field, and if you look at this field, it will behave like it follows this type of distribution. It is a highly decaying field. So this is the field in the core, and whatever field this is the field in the cladding. So whatever field enter the cladding, it may or may not travel because it is not properly optimized for propagation. It is the major field is in the core. So whatever field goes to the cladding, it accounts for the loss of the optical energy. And the field of this type, you see, is store energy, transport energy in the direction of propagation, but does not transport energy in the transverse direction. So it will not go beyond this. And one have to ensure that the optical energy should die up to this point. It should not cross the cladding, because whatever cross the cladding, it will not come back. Because at cladding, you have a cladding, you have air. There may be some reflection back. Some of our optical energy will be reflected back. But whatever goes out, it will not be reflected back. It is a complete loss. So there may be, if your core and cladding, they are optimized in such a manner that we can utilize this field, we can save this field. So this is basically, it accounts for loss of energy. So whatever energy go to cladding, it accounts for the loss. It becomes what you call as the leaky mode. So energy will be leaked to the cladding. So this evanescent field will also be important, because we will consider it when we will talk about some loss or talk about the bending loss. All the fiber, they have the bend. There is a bending radius. You cannot bend the fiber below that radius. Otherwise, this field will go out. So I will come to that part later on. So as a result, in order to secure this field, in order to look at this field, we need very optimum cladding. It put constraint over the cladding material. So the evanescent field gives rise to requirement for the choice of cladding material. It should be transparent to light at the wavelength over which the guide is to operate. Because we want this energy to travel in that direction, it should be as transparent as the core, but differ in the refractive index. Cannot differ by large values. So mostly I mentioned core and cladding, they differ in the refractive index only at the third decimal place. Then should consist of a solid material to avoid both damage to the guide. So the cladding, it should provide mechanical strength to the optical fiber. No foreign particles should enter the core cladding interface. The cladding thickness, generally I mentioned, it is 125 micron. So cladding thickness should be sufficient to allow the evanescent field to decay to very, very low value or to zero value. No energy should cross the cladding. And you know, all these fields, they have the distribution. If you calculate all these distribution of different modes, you talk about mode has this type of distribution or it has this type of distribution. If you calculate what is the diameter of the mode, all these modes we define one parameter, what is called mode field diameter. What is the diameter of the mode? And if you calculate this diameter, the diameter of this mode, the evanescent field, the falling rate part is basically your 50 micron. So you have a fiber with axis, you have 50 micron upside, you have 50 micron on lower side, and around 10 micron is the diameter. So what is the total thickness? 50 plus 50 plus 10, 110. So plus minus certain values. So core cladding diameter is always kept 125. Whether it is a core single mode fiber or it is a multi-mode fiber, the cladding thickness is 125. This is the minimum thickness which is required for the cladding. It can be more. You may come across the fiber with more cladding diameter, but not lesser than 125. And this is all based on the mode field diameter calculations. So as a result, mostly the core and cladding materials, they are of very, very high quality, and refractive index are very, very near to each other. So core is cladding is as transparent as the core, but we want the difference in refractive index also. So although it gives lower numerical aperture for the fiber, because if the refractive index or core and cladding, they are very near to each other, numerical aperture will be less. But it provides a more practical solution. We want the practically the light to travel, light to propagate. So as a result, refractive index or core and cladding, they are very, very near to each other. So I gave the concept of the mode, then different group velocity and evanescent field, and why the cladding thickness is 125. All these values are very, very important. They are all based on our Maxwell solutions or electromagnetic mode theory solutions. But practically, our optical fiber is a cylindrical fiber. I consider a planar waveguide because we know the two-dimensional problem. It is very easier to solve a one-dimensional equation. It is somewhat difficult to solve a second-order equation. It is very, very difficult to solve a third-order equation. Three-dimensional problems become more and more difficult. So fiber is basically a three-dimensional fiber. Or if it is a three-dimensional problem, we have to add more parameters. Like in the first part, we have only the m as a what you call as the subscript or argument. Now when we have a three-dimensional, we have to consider the two planes, xy plane, yz plane, and yz plane. So three different parameters are there. So I can consider x and z, I can consider y and z. So I need two variables. So like if you talk about the quantum mechanics, we talk about the principal quantum number, we talk about the orbital quantum number. That accounts for the orientation of the field. Similarly here, we have to add more parameter. So if you consider this part, cylindrical fiber, the solution become very, very complex and very, very complicated. So in common with the plane waveguide, we have different type of mode like TE-LM mode. So instead of TE and TEM and TMM mode, now I can have TE-LM, TM-LM. So value of M can be from 0 to any value. Similarly, value of L can be from 0 to any value. So I can have TE00, I can have TE01, I can have TE10. So different values are possible. Different orientations are possible. So as a result, we have the number of modes. Similarly, we have the number of hybrid modes. So we can have planar mode, transverse mode, pure TE and TM mode. We can have the mixed mode, like your HE mode, HELM or EHLM. What does it mean? So we have hybrid mode. If I write, what is the difference in HE and EM? EH. We have HE or EH. Both are same. But in that case, we know if you go to any, in the mode theory, the electric component is always more than the magnetic component. So in that case, and there is a variation. If these values are interchangeable. So if your H field is more than E field, I will write it as HE. If E field is stronger than H field, it will be EH. So depending upon which component, which field is stronger, greater. So H field or EH, so number of field will be there. But if we consider all these modes, now in the three-dimensional you have number of modes. There may be different type of permutation combination. So it is difficult to solve these equations. It is difficult to handle these modes. So naturally, when a problem becomes very, very difficult, we go for the assumptions. We put some boundary conditions. So in order for the light to be wave guided, we consider the condition, we apply the condition that let this angle to be very, very small. The angle of incidence. Let delta to be very, very small. And angle to be very, very small. Then we can have the solution. So in that case, the number of modes, they will also become lesser. Because now the light is within very small values and refractive index variation is also very, very small. So delta, numerical aperture will be very, very small. So we can have number of modes, and in that case, further in these conditions, we can look for what is the distribution of the mode. Because we are interested in power. Whether the mode is horizontal mode or it is a perpendicular mode. If the distribution is same, they will have the same power. So they will be having the same power. So we call these are the degenerate modes. So degenerate modes are the mode where the field distributions are of similar type. So then we can have a linear combination of degenerate modes. So we can club these modes and the problem will become further simplified. So we call these as a linearly polarized mode. The mode which are of having same type of distribution. So LP modes. So a linear combination of degenerate mode produces a useful simplification to the analysis of weakly guided fiber. We call these as weakly guided because delta is very, very small. If the delta is large, it will be very highly guided, but if you keep the delta, otherwise it will not be practically solution possible. So in that case, for example, if you look at these modes, so HEE1 mode, there is no other mode like this. So it is a unique mode. HE21, TE01, TM01, these modes, they are similar modes. So they can be clubbed together. So we will call these mode as LP11 mode. So LP11 means 3 modes. LP21 mode means HE31, EH11. So they can also be clubbed. Similarly, we have LP01 mode. We can have number of modes like this. We have different type of linear combinations. So different modes are there like this. So this is what is the intensity profile of all these modes. So if you look at these modes, see HE11, it is a totally concentrated mode. So power is concentrated at the center. If you look at this mode TE01, you see you have two halves. This is horizontal. Similarly, TM01, this is vertical. Similarly, HE21, it is also vertical. But if you add these halves, the total will be same. So whether it is horizontal or it is perpendicular or transverse, your power will same. So we can club these modes. So we will call these are this is a linearly polarized mode. Similarly, this component, it has 4 halves, higher order mode. If you add all these 4 lobes, the total power will be same. Because power is area under the curve, energy. So all these modes are of linearly polar. So by applying these assumptions, we can simplify the problem and we can our complicated problem, it become a solvable problem. So they have this type of distribution, E mode, H mode, and they will change orientation. When they oscillate, they change the orientations. So intensity profile. So this is how these different modes are shown here. So lower order mode, maximum intensity at 1 point. You have higher order mode, distributed power. So power at your detector, power will fall at 2 points. So naturally they will travel different distance. If the power fall at only single point, so your pulse will be very fine pulse. Whereas here there may be some variations in this point and at this point. So that lead to some maybe some variation or some degradation of the signal. So different modes are shown here. And then you ultimately what will happen if in the cylindrical coordinate I mentioned you, we have to use the cylindrical coordinates. So r, theta and phi coordinate, they have to be considered. So in general, in the cylindrical coordinate, the equation will be like this. We have the functions with the r variation, 1 over r and phi variation, and ultimately n1 square minus k square minus beta square psi. So this equation is governed by this factor. What is the value of beta? If your mode is within the core, so naturally this term will be 0. If your field is in the cladding, this will be n1 square k square minus n2 square k square. So this has then certain value, and naturally this value will be now governed by this. Your beta will be governed by n2k minus beta and n1k. The value of beta will always between these two parameters. And then we know that here the one have to add the solution in terms of the phi. So this factor will be added. So like in those who have come from in mathematics, we go for separation of variables. In any cylindrical equation, we separate the variable in terms of r, in terms of theta, in terms of z. We have different solutions, and then we will combine those solutions. So here we have the two coordinate r and theta phi. So we have this is the z dependent same part, and this is the orientation dependent. So we will have this added this term. So if you further put this solution, the wave function psi in this equation, we will end up with again the second order differential equation, but in different form. So that we will have this solution. So this is again this factor, and the L number. L number will also comes into picture. So this is a very standard equation in mathematics. What is this equation? This is a Bessel equation. It is a standard Bessel differential equation in mathematics. And the solutions is the Bessel functions. Different functions are there in mathematics. Bessel function, delta Dirac functions, Hermite functions, Legendre functions. So many type of functions are there. They have the standard solutions. So this is a Bessel equation. Now it has the Bessel function. Now again, value of beta. If the beta is chosen in the core, this is Bessel equation for core. If beta is chosen for the cladding, this is the Bessel equation for cladding. So both equations will be different, and both will have different solutions. So we have Bessel function, Bessel equation for the core, which is a gradually damped oscillator function. We have the Bessel equation, we call it as a modified Bessel function, which is the solution for the cladding, because cladding field will be different than the core field. And I mentioned when the light travel in the optical fiber, some part goes to cladding, especially in the single mode fiber. Around 20% light goes to cladding. So we have to consider how much power flows in the core, how much power flows in the cladding if we want the complete solution. So we will see this is the Bessel equation for the core, Bessel function for the core. This is Bessel function for the cladding. This is a highly decaying field, and we know the evanescent field, that is a highly decaying field. So it is incorporated here. So but if you want to have the full solution, I have to combine the solution for the core and solution for the cladding. Both have to be added together. So if you look for these solutions, these are the distribution. If you look for the solutions for the field, these are solution in the core. This is the solution in the cladding. So you will say this factor will come into picture. So core and cladding solutions. So we call these are the U and W. This is the eigenvalue for the core. These are the eigenvalue for the cladding. These are some standard solutions. And these are the parameters. You see, U can be written in terms of these parameters. For core, it is the N1 square, K square. For cladding, it is N2 square, K square. Now we have to combine these two values. Eigenvalues are basically the energy values. And if I want the total energy, total optical power, I have to club that. So I can put here like U square plus W square square root. Resultant of two vectors or two functions. So if you substitute these values, U square, U and W, I will have Ka N1 square minus N2 square square root. And this is nothing but numerical aperture. And this A is the radius of the fiber. And K is propagation constant, 2 pi over lambda. So we call it as the B number, or it is also called normalized frequency. So B number for the fiber. B number is basically value of the fiber. B number will tell me number of modes propagating in the fiber. So B number is the parameter which is only possible with the electromagnetic mode theory. It cannot be derived using the geometrical optics. So B number is 2 pi over lambda A into numerical aperture. So you can further write it in terms of the refractive index of core and the relative refractive index difference. So it is a very, very important parameter. We call it as a normalized frequency. And if you try to dimensionally check this equation, you will see it come out to a dimensionless. A and lambda both have dimension of length. So it will become a dimensionless parameter, but we call it as a frequency. Then why? How frequency? So okay, this is analogy because we know not to wavelength, but we know the frequency is inversely proportional to wavelength, and it is following the same relation without bothering for the dimensions or the principle of homogeneity of dimensions. We look simply that it is inversely proportional to wavelength, so it is a frequency. So it is sometimes it is called normalized frequency, or it is called the B number. And you see, B number, it combines in a very, very useful manner all the fiber parameters. You see, this combine A, fiber, delta is related to fiber, lambda is related to source. So B number, it combines in a very, very useful manner optical energy from the source and optical energy in the fiber. So it's a very, very important parameter which accounts for the number of modes in the fiber. But the B number, so that will tell about the number of modes. Number of mode means how much power it can carry. More the number of mode, more is the power it can carry. Lesser the number of mode, lesser power it can carry. And it is a parameter which classify the single mode and the multi-mode fiber. Differentiate between single mode and multi-mode fiber. If B number is less than 2.405, it is a single mode fiber. If B number is more than 2.405, it is a multi-mode fiber. As I said in next few slides. Then
V equal to 2.05.
2.05.
Then what will be the?
It is a single mode fiber.
Single mode. Greater than
2.405. If B number is less than 2.405, it is a single mode fiber. If B number is more than 2.405,
then what is this?
Equal to, naturally, see, we are at the cutoff. There is a line.
There is no such mode can be defined on V is equal to 2.405.
At 2.5, see, 2.405 basically we are talking about the interface. All the mode they have certain cutoff. So at cutoff value, the mode is there. Above the cutoff, value is not there.
It means that at V is equal to
The mode is there, but other mode they will cut off.
Which mode is there then?
Only one mode will exist.
Which one?
Let it say LP01 mode or zero order mode. Zero order mode will exist.
Or we are confirmed to say that there is this mode exists.
You see, when you are saying the cutoff, let us say cutoff is 70%. So all below 70% they will be considered. And 70% will also be considered. 70% or below 70%, they will be considered. Above 70%, they will not be considered. So there is a cutoff value. It can be greater than equal to 2.405. You include the equal to also. Yeah.
Sir, at cutoff value, no light will propagate through the fiber, sir.
No, light will propagate, but all the mode will not travel. Some mode will cut off.
Sir, what do you mean by zero mode, sir? Actually, we know there are two.
Okay, I will come to that point. I will come to that. Zero mode means it is your LP01 mode. When I say zero mode, it is zero order. Zero order mode. So it has Gaussian distribution. When I say M equal to 1 mode, it has 2 lobes. So when you say M equal to 0, zero order mode means only first mode will travel. And first mode LP01, only one mode is there, that is HE11.
As per the previous diagram, there are three diagrams.
Yeah. There were different type of modes. So only one mode will travel. So this is what the B number tells. So if you look at all the distribution, I say lower order mode, very narrow. Higher order mode, higher order mode, higher mode. This is just like a layer. Now if you want to cut the higher order mode, I will consider put some barrier here. Only this mode will travel. Other they will cut off. So this is in terms of the B number. They are just like this. If the B number is like follow, let us say all these modes, these are the modes. These are the Bessel solutions. And this is a normalized frequency. And if you consider this mode, LP1 mode, it comes at 0 at this value.
Sir, L stands for lower end.
These are the linearly polarized mode. There we have clubbed the degenerate modes. LP11, it is not means that it is a one mode. There may be HE11, HE22 or number of modes will be there clubbed under LP11 mode. LP11 mode means all the mode within this, they have similar type of distribution.
Degeneracy will start at this stage.
Yeah, degeneracy will come. There is no two mode under LP01 which are similar. So it is a one mode only. Here there are number of modes. Number of modes here. Number of modes here. So if I put this LP01 mode like this value is 2.405. It means only this mode will be there. All these mode will be cut off. If I put the value here, say 3.83, only LP01 and LP11 will travel. Other they will cut off. Similarly, if I put say B equal to 10, so up to LP13 mode they will travel, other will be cut off. So there is a cutoff for all the modes. And we can have this cutoff from the B number. And B number, B number is 2 pi over lambda A into numerical aperture. All these are the independent parameters. Wavelength is of source, diameter of the fiber, and numerical aperture, it will depend upon the refractive index of core and cladding. So I can control this B number. So if I want only only one mode, LP01 mode, so B have to be 2.405. B can be lesser than that. If you want let us say B equal to 0. But then no power travel in the optical fiber. No energy. It is of no use. I want some energy to travel, to flow in the optical fiber. So B number basically decide. If I want these both two mode, I will keep it at 3.83. So below 3.83, these two mode will travel, higher order mode will cut. So you understand this point? It can be less than equal to. You can have equal to also. It does not mean that at equal to no energy will be there. Because it is a continuous energy. Even if you look at this part at 2.405, some contribution of this is also there. So that's why we have variations. These are all approximations. When I say a single mode, means approximately it is a single mode, not exactly single mode. So that's why you see there are the variation in the communication part. So we have this. This is how the single, you see in brief. Shown here, you have the multi-mode fiber, you have the single mode fiber. All these modes. This is how it travels. So mostly in the single mode, you will see it is generally shown as a straight line, but practically it is not a straight line. It is a, when you have a very small narrow, there will be very large total internal reflection will be at very long distance. So it is near to straight line, but not straight line. Similarly, single mode near to single mode, not a pure single mode, because we are approximating all the things. So B number less than equal to 2.405. So only this mode will travel. This is 2.405. All these modes they will cut off. Only this mode will travel. And if B number is large, all the mode will travel. So mostly for the multi-mode fiber, B number is large. For single mode fiber, B number is less than 2.405. But again, 2.405 is a very defined number, sharp parameter. And we know there are always variations. So we will see how to fix this value. So we define, but is now I think things are clear. But when value is equal to certain parameter, beta equal to n to k, we call it as the cutoff value. If the beta is cutoff value, and if the mode is equal to block, in this case you have the imaginary solutions, so W will be 0. So mode we have the cutoff value. Now if value is more than n to k, more than n to k means in the core, less than n to k in the cladding or outside the cladding.
What is beta here?
Beta is any value of propagation vector. N into k. K is in the free space and nk is in the medium. So beta can have any value from n1k to n2k or n2k to n1, because n2k is lesser as compared to n1. So value always lies between n2k to n1k. Beta is in medium, k is in free space. For free space, speed of light is written as c. For medium, it is written as b. So multiplied by refractive index. Similarly, all parameters they will be multiplied by refractive index. So beta is in the medium, k is in the free space. So if the beta is less than n to k, the light will go outside the cladding, and we call it as the unguided mode or leaky mode. So light will leak. So leaky mode. Similarly, if beta is more than n to k, so it will be moved toward the core. So it will be a guided mode. So we have guided mode, then beta is more than n to k and equal to n1k. n1 is the refractive index of core. For step index, it is equal. For gradient index, it is variable.
सर आपने मेंशन किया है लीकी मोड जो है वो अनगाइडेड मोड है.
Yes.
जो दूसरे वाला वो गाइडेड मोड है सर.
Yeah.
तो लीकी मोड में तो सर एनर्जी का लॉस नहीं होना चाहिए.
हो जाएगा ना? See, in leaky mode, you see, beta is less than n to k. Okay. Means outside the cladding. Leak हो गया. That's why it is called leaky mode. It may leak. Leaky mode. It will not reach at the destination. We want guided mode. The mode has to be guided mode. Then it will reach at the destination. So we avoid this condition. So we have the leaky mode. They are also called radiation modes. Radiation mode means what will happen if the light is incident at the core. In the core, some light will enter in an angle within the surface angle, but what about the other light that will also enter, but they will not travel by total internal reflection. So we call it as a radiation mode. It will leak at that point only.
Two rays are axial or marginal rays.
Yeah. Opposite. So the range of beta will signify the guided mode. So guided mode and leaky mode or unguided mode. Unguided mode may or may not reach at the end, but guided mode they will reach at the end. So in single mode fiber, in single mode communication, we choose the guided modes. So any disturbance, now I mentioned about guided mode or leaky mode, any disturbance in optical fiber, it may convert from the guided mode to unguided. So that's why the fiber, we want a perfect fiber. Any variation may be in the deviation in the fiber axis, in the straightness, or variation in core diameter, or irregularity in core cladding interface. It has to be straight line. If there is a variation, the critical angle condition will not be fulfilled. So they all lead to change in propagation connectivity, but we call it the mode coupling or mode mixing. So coupling means some form of energy will be transferred to the another mode. Yeah. So that energy may travel or may not travel. If it will not travel, it is a loss. It will travel, it is a gain. So leaky mode can also be coupled to guided mode, or guided mode can be coupled to leaky mode. Both possibilities are true. So mode mixing, one have to avoid it. So we need a perfect fibers. So we have the step index fiber, we have the gradient index fibers. So here, in basis of this, we have single mode fiber, we have multi-mode fiber. So another parameter is we have the step index fiber, we have the gradient index fiber. I will come to this point. So I can have a single mode step index fiber. I can have a multi-mode step index fiber. I can have a multi-mode gradient index fiber. I can have a single mode gradient index fiber also. But mostly gradient index fiber, they are the multi-mode fibers. Because it is not that it is not possible. It is a practical problem. In the gradient, if it is a single mode fiber, the diameter cannot be more than 8 micron. Or changing the refractive index within 8 micron is very, very difficult. It is near to impossible.
There is sharp boundary between core and cladding.
There is
sharp boundary between core and cladding in this type of fiber.
Yeah, sharp boundary between core and cladding is there, but even the refractive index within the core changes. It is maximum at the center. As you move away from the center, it goes on decreasing, and finally it will merge with the cladding. So I will show you in the next slide the variation. These are the constant refractive index fiber. These are variable refractive index fiber. So mostly looking at the practical difficulties, the gradient, the communication gradient index fiber, they are the multi-mode gradient index fiber. I will tell you, there is another benefit in the gradient index fiber. The dispersion is very, very small as compared to step index fiber. So, and here you will see mostly for the multi-mode fiber, the dimensions are maybe from 50 to 100 micron or even less than that, whereas dimensions are from 8 to 12 micron. Core is 125, cladding is 125. Here the cladding may vary depending upon the diameter. So we can classify the fiber as single mode fiber, multi-mode fiber on basis of B number. We can classify the fiber as step index fiber, gradient index fiber on basis of refractive index profile. What type of profile it is? Refractive index is constant, step index fiber. Refractive index is variable, gradient index fiber. Here is a gradual change in refractive index. So step index fiber, I mentioned, is a fiber with constant refractive index. So there is a step change. These are refractive index of core, these are refractive index of cladding. There is a step change in refractive index for core and cladding. So step index fiber. Here the light follow different path. This is the multi-mode. Number of modes are there. So this mode enter at very, very small angle. It goes straight up to long distance. This mode enter a large angle. It cover very small distance, undergo total internal reflection. So it can be taken as a straight line, but it cannot be taken as straight line. So then in the single mode fiber, you see this is a very, very small angle. So it is considered as a straight angle. But practically there is a total internal reflection, but it is very, very near to straight. So we have the core of refractive index N1, core of cladding of refractive index N2. So multi-mode step index fiber, single mode step index. These are the modes in the single mode fibers. So we can calculate how many modes are propagating. That is in terms of the B number. So B number will tell me how many modes are there. So if I will not go into detailed theory, this is all based on different theoretical calculations. The total number of guided modes. We will talk about the guided modes only. So guided modes, it will be given by B square by 2. So if you know the B number, you can calculate the how many modes will be there. So B number can be calculated from the wavelength, from the radius of the fiber, from the numerical. So one can calculate if you have a multi-mode fiber of 80 micron diameter, and this is the refractive index, more than around 3000 guided mode will travel in the multi-mode fiber. Because here A will be large. So large number for multi-mode fiber, B number is more. This is the power flow. You can calculate how much power will flow in the optical fiber. And again, you know the power flow, it is again given by what you call the Poynting vector, 1/2 E and H cross. So one can calculate this from electric field and magnetic field, how much power flow. And so this power also depends upon the B number. B number will also decide how much power will flow in the core, how much power goes to cladding. So P clad over P, this is 4/3 M 1/2. M is the mode number. And we know M number is proportional to B square by 2. If you substitute value of B here, so ultimately your P clad of P will be inversely proportional to B number. So larger the B number, lesser power in the cladding. Smaller the B number, more power in the cladding. So what is my need? Less power in the cladding. Any power which goes to the cladding, it may or may not reach at the end. But any power which is in the core, it will reach, it will be guided mode. So B number is, this is the reason you see, if B is around 1, 70% power flow in the cladding. If B is 2.405, around 20% power flow in the cladding. So when you have a single mode fiber, for single mode fiber, B is equal to 2.405. So around 20% power goes to the cladding, 80% power goes to the core. So single mode fiber, they are more sensitive to bends. Multi-mode fiber, they are least sensitive to bends because there is no power in the cladding. So this is how, again, the diagrammatically you can find P clad or P for lower value for B number. If B number is around 2.4, so it is the 20%. If it is less, more power goes to cladding. And this is the P core. So they are all related to, and they are mode dependent. Different mode, they will contribute differently. For different mode, B number is different. Similarly, we have the gradient index fiber. So in the gradient index fiber, they do not have constant refractive index. The refractive index goes on decreasing with the radial parameter R. As you move away from the axis, the refractive index goes on decreasing. So they are also called inhomogeneous core fibers. And the refractive index variation is given by N1, 1 minus 2 delta R over A alpha 1/2. A is the radius and R is the radius parameter. It varies from 0 to A. Value of R is 0 to delta is, you know, the refractive index difference. And for cladding, it is constant, N2. This alpha is very, very important parameter. We will call it the profile parameter. What is the type of distribution of the profile? And we can relate this is the profile value. If alpha is 1, your profile will be triangular profile. If alpha is 2, it is called the parabolic profile, or also called Gaussian profile. If alpha is large, say around 10, it is near to step index profile. So alpha parameter is important for the gradient index fiber. And this is very, very important when we consider the dispersion gradient index fiber as a dispersion point of view. And this is how the light travel. The gradient index fiber, basically they are designed to overcome the multi-mode dispersion. When you have a number of modes, they cover different paths. They follow different paths. And when they will follow different paths, they are moving with the same speed, they will reach at different time. But in the gradient index fiber, they will reach at the same time. Because in different regions, the wave moved with the different speed. Here, the refractive index is maximum, so speed will be less. Here, the refractive index is minimum, the speed will be more. So the mode will be travel here. It will cover the shortest distance, but it is moving with the slowest speed. The mode which is traveling along this path, it is covering the longest distance, but it is moving with the highest speed. So they will reach at the same time. So in the gradient index fiber, the intermodal dispersion is very, very small as compared to step index fiber. So mostly for the multimode propagation, we use the gradient index multimode. So, and profile the parameter we already discussed. Similarly, we define different parameters for a gradient index fiber. We define the parameter numerical aperture for step index fiber, n1 square minus n2 square. But what is n1 in gradient index fiber? You don't know. It is a function of R. So it had difficulties. How to define the numerical aperture? Where all your B number, other parameters, they are based on that parameter. So dealing with step index fiber is much easier as compared to gradient index fiber. But of course, there is a need. Step index fiber cannot provide you very, very high data rate as compared to gradient index fiber. So we define the two variable parameter. One is the local numerical aperture, where we will use n square R. So depending upon the dimensions of the fiber, we can find what is the R. So it can be evaluated as a function of R, then axial numerical aperture near the axis. So it can be n0 square minus n2 square or little. So two numerical apertures are the axial numerical aperture and local numerical aperture. We can evaluate it by using different parameter, and of course then we can, looking at different positions, we have to add it. So gradient index fiber and the number of modes. Here the number of modes is given by these parameters. Alpha over alpha by plus 2 over b square by 2. So naturally here the number of guided mode will be less. B square by 2, alpha by 2. If alpha is 1, it will be 1 by 3. If alpha is 2, it is 1 by 2. So lesser number of mode, easier to handle. It is just like a traffic. If there is less traffic on a road, you can move very easily. But if there is more traffic, there will be a lot of collisions. If there are more modes, there is more transfer of energy, more mode coupling. So gradient index fiber, there are lesser mode and lesser path difference, or as a result, lesser intermodal dispersion. So on this basis, we have the different type of fiber. We have the single mode fiber, where only one mode will travel. B number is less than equal to 2.405, and they are most important for long haul use, carrier or internet core. The dispersion is least in the single mode fiber. In fact, there is no intermodal dispersion because there is only one mode. No chance of collision. Only one vehicle is traveling on an expressway. No loss of energy. They are small core, 8 to 10 micron, and that forces these to be used with the lasers. So mostly we need a compatible source, and lasers are the narrowest source of optical. So laser light sources, they are most expensive and delicate to handle because of the core dimensions. Highest bandwidth. Bandwidth depends upon the broadening. Least broadening, so highest bandwidth. So they can cover a distance rating of more than 100 kilometers without any regeneration. We have multimode fiber, which are relatively larger core diameter, maybe 50 to 100 micron. They are easier to couple. Diameter is more, so light, very easy to couple. If both are narrow, they are difficult to couple. They are step index multimode cables. There are gradient index multimode cables. I mentioned in the step index multimode cable, the broadening is more or dispersion is more. So they can give, they will give you lower data rate, around 50 Mbps. For gradient index fiber, they can give you, there is no intermodal dispersion or very small intermodal dispersion. So as a result, they can give you high data rate. We have the single mode step index multimode fiber. We have the gradient index multimode. So these are the designer's parameter for which this lecture was there. So I should know what are the parameter of the fiber. If you go to the market, you have to purchase the fiber. You should know what are the parameters. Just like diode or transistor or like ICs, there are certain parameters. Similarly, I need certain parameters. I should know what is the numerical aperture of the fiber. I should know what is the delta. These are provided parameters. These are the parameter or specification of optical fiber. What is the normalized frequency, B number? Of course, we can calculate it from the dimensions. But these parameters are designer's parameter. A designer should know what is these values because he have to calculate. He needs some data for designing of the system. Without data, he cannot design. Cutoff wavelength. I mentioned the fiber is single mode. If the wavelength, if the B number is less than 2.405, now B number is 2 pi over lambda. So it is also related to lambda. And lambda is the wavelength. What is the cutoff wavelength? If lambda will increase, B number will fall. If lambda will decrease, B number will increase. So decrease in wavelength, increase in B number. So your fiber will become a multi-mode fiber. So a single mode behavior will be converted to multi-mode behavior because of change in wavelength. So there is a cutoff. Wavelength should not fall below that value. That is the cutoff wavelength. So lambda c is the wavelength above which a particular fiber become a single mode fiber and below which the fiber is become a multi-mode. So cutoff wavelength. Similarly, power distribution. Power distribution will be, if B 2.405, 80% power flow in core. And if B is 1, 30% power flow in core. 70% power goes to cladding. It means you have a risk of 70%. Very risky, very risky environment or unguided environment. Your system will not operate. So we always work between the two values. So B number is not too large. You cannot take very high risk. Or if you have to earn something, you have to take risk. If you will not take risk, you will not get the profit. It is just like a share market. You can go for normal deposit, you will get only say 5% or 6%. You enter the share market, there is a risk. You may get 15% or you may lose your amount. So risk has to be taken. So here, but it should be within certain range. It's not be very totally risky, and it should be certain limit. So as a design compromise, a designer is always keep the B number between 2 to 2.405. So it is within. So you are at the center of the road. So both these values. So B number is also very important for the power distribution. So this is also another parameters. So these are all designer's parameter which one have to, which you see, which have been derived using the geometrical optics or using the electromagnetic mode theory. So it is not that we can skip these mode theories. Otherwise, we will not understand what is B number, what is the role of B number, how it has been derived. Similarly, cutoff wavelength. power distributions, all they come from these purpose. And I should know what is the power distribution within the fiber. Then only I can understand the light propagation. So we have different type of fiber. These are application area. Single mode fibers, mostly these are the step index type. It is not that they cannot be graded index, but for practical application, for technical point of view, they are the mostly the step index fiber. For cost point of view, if you will go for the single mode grade index fiber, it will be very, very expensive. So they are ideally suited for high bandwidth application or long haul application, mostly telecommunication. And they are mostly used with the injection laser diodes because these are coherent sources. Similarly, multimode fiber, they are step index fiber, they are grade index fiber. Step index fiber, more dispersion. Grade index fiber, least dispersion. So in order to get the minimum dispersion, one move from multimode step index to grade index or to single mode fiber. So step index fiber, they are best suited for long haul application, limited bandwidth, relatively low cost applications, whereas grade index fiber, they are best suited for medium haul applications. So there we use the multimode fiber, and they can be used with the LEDs or with the lasers, and mostly for the local area application or medium haul application. So LAN or MAN networks. So we have different type of fiber which can be used in different environments. These are application oriented. It is not a one fiber which is used for all the applications. Lot of varieties of fiber are available because we have to optimize the system. We have to create a cost-effective system. We have to look for a economical system. In this competitive market, no company can enhance the call rate on the telephone. In BSNL, it is 49 paise. If any company reduces, most of the users, they will go to that company. So it is again, that's why there are regulating bodies. So these are all application areas of optical fiber. So different type of optical fiber I mentioned here. We have the single mode fiber, we have the multi-mode fiber, we have the single mode step index fiber, we have multi-mode step index fiber or multi-mode grade index fiber. And all these parameters, you see, it is not only the single theory which work in the optical fiber. We have to understand the geometrical optics. We have to understand the electromagnetic mode theories. So all these parameters, they are required if you have to understand the propagation of light through optical fiber, or one have to go for the link design using the fiber optic link. So I will stop here. So in case you have any doubt or any query, you are most welcome.
What is the basic difference between modal dispersion and wave-wide dispersion?
Modal dispersion is the dispersion of mode, and this may be because you will come. We have intermodal dispersion, we have intramodal dispersion. So when you come to single mode fiber, there is only one mode, no intermodal dispersion, but still there is broadening of the signal. How it comes? It comes from two parameters. One is the material dispersion. The refractive index changes because of the wavelength. I consider it as in the group velocity. So it is n1 d n1 over d lambda. So I consider the first order. Higher order I neglected, but they are not zero. They contribute. So single mode, we call it as a material dispersion. Similarly, now light group velocity. So we taken as dn1 over d lambda. What about dn2 over d lambda? Because in single mode fiber, light 20% light goes to cladding. So group velocity will be different in cladding and core, but we only define the group velocity. So what is the spread in group velocity when it in core and cladding? That is called the waveguide dispersion. It is because of the structure of waveguide. So waveguide dispersion and modal dispersion is the general intermodal dispersion or total dispersion. Okay. Any other query? So any question from nodal centers?
Nodal centers.
Any query from nodal centers? So I explained about the basic optical waveguiding phenomena, different parameters and different classification of the fiber on basis of modes and on basis of refractive index profile. In case you have any query, you are most welcome. So there is no question from any of the nodal center.
No, sir. Thank you.
So should we stop here?
Good evening,
Yes,
sir.
sir.
Okay, good evening. So from tomorrow we will start at 9:30. So we have two sessions.
Good evening, sir.
Good evening. Good evening. You have any query?
Sir, are you hearing me?
Yeah, yeah.
I'm
hearing
from
you.
PSS80 Noida.
Okay.
This query is related to the V number. We also teach this topic, and we also use this number 2.405 as the cutoff.
Okay.
But the thing is, how is it exactly derived? Can you, I mean, we can do it later, maybe in some other session. So can you explain this properly?
So see, B number, basically B number, it will relate how the waveguide in core and cladding. So I mentioned about the Bessel equations. Bessel equation for core and Bessel equation for cladding. So if you want to total power, because power is flowing in core and cladding, if you want the total power, that is related to B number.
Yeah, okay.
So B number comes as a solution of power in core and cladding.
Okay. How does it indicate the cutoff mode as the number we use 2.4? How does that come? That is a question which we want.
Okay, let me show you this one slide. You see in this slide, if you see, you see this is the value here. If you look at this figure, now we have number of modes, and if D is 2.405, so all higher order mode will not be there, only one mode will be there. So this forms the cutoff. There is a cutoff for different modes. Am I right?
Yes, sir.
Or you can look at this diagram, this solution. This line is a cutoff. All these mode LP01. So if I put the B number here, all these higher modes they will be cut off. If I put B number here, these modes they will cut off and these modes they will travel. So it is a deciding parameter to cut the mode.
Okay, sir.
I hope it is clear to some extent.
Yes, sir. Thank you, sir.
So any query from other center? हरजोत कोई बैठे हुए हैं? देखिए ICT में थोड़ा जेवी. Okay. So I will stop here. So from tomorrow we will divide the session in such a manner that we will start at 9:30 to 11. Then there will be half an hour tea break. Then 11:30 to 1. And in the afternoon we will start at 2:30. So 2:30 to 4:30. This is what we have planned. So tomorrow I request all the coordinator and at nodal center to come around 9:30, so that we should be able to start the session some little bit early and finish within the specified time. Okay.